Unpause the recording.
Cool. All right. Good. So we can actually get this going. Awesome. Yeah. So just I'm currently in my lab right now, which is why I'm wearing a mask today. So hello, everyone. This might not be every day of the week, but it's just my internet at home is a little bit spottier, so I'd rather do it from here so we don't have any problems. If you have any problems hearing me, just let me know and I can enunciate more. Yeah, so thank you all for coming. I feel like we might get some more people streaming in as we kind of start here. Yeah, so this is the CATS tag data processing workshop. And so hopefully you all have signed up because you are maybe interested in CATS tags or interested in inertial sensing tags in general. And so we're going to kind of get into a little bit of what we're going to be going through this week. So I'm going to start by sharing this screen. Okay, so this workshop is going to be going all 5 days this week, and we're essentially going to be going from 10 a.m. to 1 p.m. Pacific time every day, with some time later on in the afternoon for questions and things like that. So we're basically going to make ourselves available. So if anybody is following along with us and wants to keep up or is having difficulty in some way, that'll be the time to really get at us in a more personalized way. So to start, I am Will Gough. I am one of your two sort of main instructors for the workshop here. And I am currently a fourth year PhD student in Jeremy Goldbogen's lab at the Hopkins Marine Station associated with Stanford University. So I'm in Monterey, California right now. I'm sort of coming at this as a sort of like an intermediate user. I came into the lab, I didn't really have any tag experience to start, but I've now spent about 3.5 years working with these tools and working with this data and trying to figure out ways to essentially use inertial sensing and orientation to figure out how large whales swim, how they eat, things like that. So some event detection, which we'll get into later, some different things like that. And our other instructor is Dave, who you heard from a little bit before, those who were here a little bit early, and I'll turn it over to him to introduce himself.
Yeah, thanks. My name is David Cade. I was a PhD student in Jeremy Goldbogen's lab as well. I'm now a postdoc at the University of California, Santa Cruz. I know this is a weird times, and so we're just going to kind of keep plowing ahead to do all this, but I know in particular we're asking a lot of you guys to kind of interact with Zoom and other software and things like that, and we'll keep coming back to those themes. But we're super excited to be able to share some of these tools that we've been working on for a lot of years. And so we'll start with a lot of the introduction stuff today, and kind of frame a lot of the work we're going to be doing with a lot of the hardcore coding happening over the next few days. But we'll start doing some MATLAB stuff this morning. We'll also have a lot of cool guest speakers that we'll get into here.
Okay, so just some general information. And all of these presentations will be up online on the Google Drive under the workshop materials folder. So if you need these at any time, we'll pretty much be trying to put everything up there so that anyone can use it at any time you need. So again, like I said, 10 a.m. to 1 p.m. Pacific time every day, which is 1800 to 2100 UTC or GMT, with a later sort of question and troubleshooting session from 2 to 5 p.m. Pacific time. So the Zoom sessions, as we saw at the beginning there, they're going to be recorded every day, and we're going to post them online afterwards. We've had quite a few people ask us if we were going to make these available for later for people who are in different time zones and won't be able to join us live. So those will be up there also in the Google Drive folder. And so this workshop is going to be focusing on the use of CATS tags, which are customized animal tracking solutions tags for those who haven't heard of them. So we're going to be focusing on using the CATS tags and also the implementation of these MATLAB-based tools that Dave and others have come up with and really created to synchronize the inertial sensing sort of accelerometer data that comes off of these tags together with the video and acoustic data that also comes from these tags. And so I actually have one of them here for those who can see me. It's these small little tags, and we'll get into really kind of like what's inside of it and what it's able to do. And finally, one other quick note here, registration is free, but if anybody is interested and sort of willing and able, any donations that you could put toward this workshop will go directly toward a high school internship program that Hopkins has set up with the nearby Salinas High School, which is in an underserved community. Many of the students have never seen the ocean, even though Salinas is roughly 15 miles from the ocean. So there's a lot of opportunity to sort of bring these students to Hopkins and have them interact and work directly with some of the graduate students. And we have had a lot of success with this program. Students basically go through and perform a sort of a mini research project from beginning to end. We sort of supply the idea and some of the data, and then they work through it. And then at the end, we have a small symposium where they can present their data to each other, to their parents, to us. It's very fun and very rewarding. And the goal is to make that a paid internship for these students. So any donations will go toward that. And that program has actually been going for about, I think, 6 or 7 years now. Dave was actually the one that started it. And then when he graduated, he sort of turned the reins over to me and one of the other grad students here at the station. And we've been running it ever since. And special thanks here goes to Mark Lammers and the Hawaii Humpback Whale Sanctuary Foundation for really sort of like kickstarting this workshop and this idea. He came to us and said, hey, you know, we're interested in learning how to use these CATS tags, and would you be willing to, you know, create a little workshop? And we thought that was a great idea, and we thought, hey, you know, if we're going to do that, let's just run with it and make it available and open to whoever wants to work with these tags. So a lot of support to them, and thank you. Also, like I said, I'm in Jeremy Goldbogen's lab. Dave is currently in Ari Friedlander's lab. And the members of both of those labs have been a huge help, sort of getting this code up to snuff, getting it ready for prime time here, working through things with us. It's just been wonderful. And then the contributors to our GoFundMe, again, for our Salinas High School internship program, we're currently at $810 last time I checked, which I think was yesterday. And then our guest speakers, we're going to go through, and you'll see there's quite a few, which is really fun for us. And I think it'll be fun for you guys too, because it means there's less of me and Dave talking the whole time, which will be nice to get some other voices. And finally, all of you for joining us. It's hopefully going to be a really good time. So just a little sort of fun background on who's actually here. We have 10 different countries represented. The vast majority are in the US, but we have, I think, attendees from 5 different continents, which is pretty cool that there's a lot of people around the world working with these tags. And then in terms of the sort of affiliation or quote unquote level of the attendees, about half of you guys are graduate students, either master's or PhD. Another roughly quarter are professors or PIs. And then we have a pretty large contingent of postdoctoral students or postdoctoral scholars. And with the rough other quarter being independent researchers or government researchers and we have a category other in between, which essentially is if you're an undergrad or you're currently between positions. And if anybody here is worried that we all know what we're talking about and we all know how to work with these tags perfectly and everybody else around you knows how to work with these tags perfectly, I would like to tell you that that is not the case. Roughly 50% of the people at this workshop that will be attending here have no experience with inertial sensing. So if you've never even heard of inertial sensing, don't worry, you are not alone. Our goal is to go through that and be able to get you up to speed on that. And then another thing in terms of MATLAB experience, again, if you have never worked with MATLAB at all, if you've never even heard of MATLAB before this, don't worry, there is a very large contingent of people here who are in the same or similar boat to you. So we will be working through how to sort of set that up and get it going. And to that end, we're going to be having a small MATLAB seminar today at 2 p.m. for anybody who is interested and would like to sort of figure out how to set their MATLAB up in the proper way for what we're going to be using the next few days. And I'd like to give one more large shout out thank you to Sumit Tandon and the other folks at MathWorks MATLAB who have been really, really great working with us and sort of getting this set up, getting some of those trial licenses that some of you have or will be using here. So that's been a huge help. And so just very quickly, I sort of held this up before, but let's just have sort of one little slide here to go through what is a CATS tag. So like I said, it's customized animal tracking solutions. This allows you to, let me see if I can get this little video to play again. It includes a whole bunch of different sensors. So we have these inertial sensing units, which we'll go over what that really means. They also have cameras. Here you can see the little camera at the front of this one. They have hydrophones in some of them, some of the newer models, pressure sensing, temperature sensing, light sensing, all different units are in here. So it's very sensor rich. And what we do, as you can see in this little diagram here, but also in this video that I keep having to start from the beginning, you can see Dave on the pulpit of a small boat there with a long pole and the tags on the end of the pole. And what we essentially have to do is wait for this whale to come up to the surface. And when it does, we zoom up next to it and we slap it on its back. And we have 4 suction cups on these tags on the bottom. So that allows it to stay for roughly a day. So that's our brand of tag. That's what we typically use. But on the 5th day of this workshop, we're actually going to be hearing from some people who work with different types of tags or different sort of variations on this to potentially stay on longer or collect different types of data. And so just to very briefly go through, the syllabus should be available on the website. So if anybody has any problems finding that, let us. So on day 1 today, this is going to be our introduction. We're really going to be going through, what does the data look like? What can you really do with the data? What are inertial sensing units? What does that really mean? And so we're going to have a small video from Peter Kraft, who's one of the engineer developers at CATS, who actually helps create these tags. We're also going to be having a small talk from Ari Friedlander, who has been tagging for years now and is one of the I think sort of world's best taggers. I would maybe hazard to say. And then finally, Sumit Tandon, again at 2 o'clock today, is going to be going through sort of a mini MATLAB seminar to get this all started. And then day 2, we're going to be talking about how to sort of input your data and then actually calibrate both the tag and the data itself. And So tomorrow we're going to be having a small talk from Jeremy Goldbogen, who's my advisor and Dave's PhD advisor as well, on sort of the history of biologging, where some of this really came from with the small little TDRs and things like that. Okay, so day 3, we're going to start to sort of generate the PRH file, which is the main data packet that we use for a lot of our analyses. So PRH stands for pitch, roll, and heading. So if we're thinking about a tag, we have the 3 axes of motion of this tag. So we have the pitch of the tag, we have the roll of the tag, and then we have change in heading as the tag is moving through the environment. So that kind of gets us our orientation of this tag at any given time. And actually, not just the orientation of the tag, but the orientation of whichever animal it is currently attached to. And we'll figure out how to sort of generate that file. Okay. And then on our 4th day, we're going to go through a little bit of how to work with the video and the audio, as well as how to sort of audit the PRH for behaviors of interest. So if you're interested in, when does a whale lunge feed, or you're interested in, how often does a whale, fluke through the water, things like that. We'll go through sort of how to perform some secondary analyses after you have your data packet. And that day we're going to have quite a few guests. We're going to have Sherelle, who's in Jeremy's lab with me currently, talking about some event detection for large whale lunge feeding. We're also going to have Stacy DeReuter from Calvin University talk a little bit about the development of tag tools and sort of the D-tag, which was another iteration of these IMU sensor tags. We also have some students, Emily, Sarah, and Ariana from UCSC, so University of California, Santa Cruz, talking about using Boris, which is a small program you can use to actually perform some video audits of this data. And then finally, we're going to have Jen Tackaberry from Moss Landing talk a little bit about working with TrackPlot, which is what we use to create some of these pseudo tracks of the animal's motion. And then finally, day 5, like I mentioned a little bit earlier, we're going to be talking about some other tag types. So not just the CATS tag, but how you have some medium duration tags, or if you're working with the D tags or things like that. How that might work. And that day we're going to have James Falbush, who is another member of the Goldbogen lab, talking a little bit about his medium duration tags and working with different tag sets. We're also going to have John Kalmakidis from Cascadia Research Collective talk a little bit about working with a variety of different biologgers and how that sort of works in a historical context. And with that, I think I'm going to turn it over to Dave for sort of the second part of the introduction.
Thanks, Will. That was awesome. Yeah, I think I know people are. This is good. We got a lot of stuff to present, so I think it's worth really spending a lot of time getting into some of the real. The meat of it all and kind of setting up the motivations for all of this. So I really appreciate you guys all just being here and being willing to be engaged and stuff. And we're already a little bit running behind our schedule, but it's okay. We're gonna get through this all. It's gonna be exciting. So we'll get there all. I want to take a little chance to get you guys stoked about our some of the work that we're doing that Will just introduced so nicely, and some of the things that are upcoming, so we can kind of think about why are we doing this work and why are we involved in all of these things. And then we're going to break it out into breakout rooms here for you guys in a second. I want to start with actually this first question here. So Will talked about at 2 o'clock today, we're going to have an actual, like a second part of the workshop, which is an introduction to MATLAB for anyone who has never really used MATLAB before, or even if you just want a refresher on what MATLAB is and what it can do. And we have Sumit Tundon from MathWorks actually coming in to lead that workshop. So I just want to do a quick poll. This is me trying to be an expert Zoomer. whether you think you're going to be there, so I can give Samit a sense of whether you will be at this workshop this afternoon, so we can give them a sense of numbers for that, so we can get a sense of how many people are going to be there. So you should have a poll pop up on your quiz, and you should be able to see that. So we'll give that you guys just a couple minutes to be able to like throw up in there, just so we know, get some numbers for Samit about how many people will be there. Thank you guys. I see the numbers coming in. That's fantastic. That looks like most people. We'll leave this up for a second as I kind of go to the next stage here. We'll leave that poll open. Okay, so Will introduced us a little bit. We've been working together for a long time in the field. We've been through many variations of CATS tags. One of the things I want to make clear for a lot of this is that I've been working with CATS tags for a long time, but I don't mean to pretend to be an actual, like, the expert on all of this. Like, a lot of what we're trying to do is to present some of the work that we've done and share the work that we've done so that other people can use these CATS tags. But we also really want to like put this work out there in a format that other people can say, oh, okay, let's improve on that. Let's make this part better. Let's make that part better. Let's really get going on this thing. And like, well, that's why we're trying to use GitHub, so we can get people to actually make edits for that. Okay, thank you. So we got about 30 people come in today. That's perfect. So that was my expert to be, one of the benefits of all this, quarantine stuff that we're going through, certainly in the States, and I know all around the world, in different effects, is that we're getting better at Zoom. We won't really get into how Will and his cat Zoom bombed me in my wedding earlier this summer. We can save that story for later in the week, but we'll come back to that. I do want to give a bunch of shout outs. So none of this work is really done in a vacuum, as Will said. We are all like, it's all a long-term collaboration process of testing and acceleration and really getting all these things up and running. So there's just us working on a lot of different tag stuff. We have Ari Friedlander talking today at 12:45, right towards the end of the workshop, coming in, talking a little bit about biologging. Jeremy Goldbogen talking tomorrow morning, talking about some of the history of biologging. We've got John Kalamakitis coming in on Friday to talk about some applications and management applications. We're also going to put these guys in a panel with James Fallbush on that same day, right after John's talk. If you want to ask him questions about like ethics of tagging, or what are some of the best tags you guys have worked, or basically like we have some of the big names in biologging out there, trying to get them together. So if you guys can have, that should be an exciting way to have a interactive panel for you guys. If you guys have any questions you want to save up for that last day to ask those guys. Just really shout outs from people all over the world as we work through these things together to come up with these ideas. And I want to talk about some of the motivations for this. This is from a deployment, the very first deployment I ever put on a whale myself. And we're like, get this tag back, and this whale's not really doing anything. It doesn't feed, it just kind of surfaces. The tag's in a kind of an off-kilter location. You can't really see much of what's going on. But you see this, sorry for that sound there, that's awful. But that's a whale lice walking around on the side of that humpback whale. And you can see these other whale lice comes in there and start to, basically their interaction. You have this whale lice interaction on that animal as you're going. And so one of the first things we started to see is like, there's a lot going on in these videos that really gives you a power of these videos besides just even what you're looking for. Every time we put a tag out, we see something new and exciting. Whoa, like that. That's a remora swimming along the side of that blue whale that just kind of like fell off that blue whale. This is one of the first blue whale deployments we'd put one of these CATS tags on, and you have this like, basically this like video bombing remora coming along in there. And one of the powers of these CATS tags is that we can compare what these remora's actions are to what the whale is doing over time. And so a lot of what this workshop is going to be about is about trying to integrate the video and the data and understand some of what the whale behavior is, come up with techniques to understand what the whale behavior is so you can interpret what your tags are doing over time. We just finally turned this first deployment out into a paper. Brooke Fleming was the lead author in that. She did some really awesome work with CFD and remora suction cup feeding, suction attachments to really put out this really nice paper on remora suction. Now, a lot of the work on biologging, as Will said, comes from a long history of animal tag started by Mark Johnson in New Zealand, and who's been at Woods Hole, who's been all over the place. So if you want to get into a lot of the details of this, the purpose of this workshop isn't to be highly quantitative. We'll do some quantitative stuff and we'll do introduction to MATLAB, but the purpose is really to try to give you guys tools to get the data from the raw form to this like processed, exciting form. And Mark really kind of led the way with a lot of like making these tools accessible. So when I started, I like started with these like raw data, raw numbers. If you want to get into it, I'd recommend this tutorial that Mark put out. But we're not gonna get into the, you know, I'm a history of a math teacher. I was a math teacher before I got into science. And so I would love nothing more than to spend the whole time working on matrices and sines and cosines, but we won't be doing that this much workshop. We can always come back to that. We can always get some detailed questions later. But luckily, Stacy and Mark have worked together with a couple other people to really craft a lot of these tools into tag tools. And so Stacy's going to come in on Thursday and talk a little bit about some of these applications. And so what Stacy's work, a lot of what the tools in the animal tag tutorial does and how our workshop differs from Stacy's workshop is that a lot of what Stacy does, those tools are often designed to like help with you once you have your data in a kind of a processed form. You can use a lot of the tag tools to really like take that to like, okay, how do I filter my data? How do I separate static and dynamic acceleration? We're not going to get into so much of that. Our main goal is to get the data from the raw form into this processed form and kind of really understand and make that super accurate and super accurate and super usable. But you can do all kinds of things with these data. This is Paulo Segre did some work on from some South African deployments, looking at how humpback whales use that was a hydrodynamically active flipper stroke. So that was a side product of something we never thought we'd see on these tags. He's then used the tags to look at how the different aspects of the animal, like the flippers and the skull and the jaw, all relate to that accelerometer data. So that's one thing you can do with your CATS tags data. One of the things Sherelle has done that she's going to talk about on Thursday is looking at how the filtering time, this is a blue whale lunge feeding, and she can use the cameras to actually time the filtration in relation to what the kinematic signature of that whale is doing over time. So you can look at how that pouch, that ventral groove pouch, deflates as the data, as the whale is showing its data signal. So then you can take data that you don't have cameras for and apply that information now that you know how long the filter time's going. So Cheryl's going to talk a little bit about event detection on Thursday. One of the things that Will's been working on that he hasn't talked about yet, but is this idea of looking at fluke strokes and looking at how you can use the cameras to actually then give information about the fluke, about how the animal is actually moving through the water, how you can get some additional information in addition to the accelerometer signal. So one of the things we're looking at here is the peak-to-peak amplitude of a tail signal, which means like how much that tail goes up and down with each stroke. The reason we could do that is because we had a tag slide to the back of this whale and actually end up on the tail. And so you can actually look at how that tail amplitude changes over time. So again, every time we put out one of these tags, we see something new and crazy. And like this is one of the things that happened, and we have some new information about that. Sorry if you're prone to motion sickness. One of the things that Emily's going to come in and talk about on Thursday, she's working on a nice paper with about blowhole dynamics. So looking at how you can look at how an animal inhales and exhales and the timing and aperture of those blowholes and compare that to its kinematic signatures and its lunge feeding events. And she's using a program called Boris to do a lot of the audits for this. And so we're going to have Emily and Sarah and Nicole are going to come in and talk a little bit about Boris on Thursday at 11:30. And so that's like a video auditing step. So once you have all of your data kind of processed, you can do these video auditing steps. One of the things they've done that for, Jake and Nicole and others have done this project on minke whales, looking at how when minke whales surface, they can keep track of the researchers. Oh, sorry, no, wrong one. They can keep track of the ice concentrations in the water. So they can actually you can actually use this video to look at what is the minke's environment looking like? How is the minke whale using its environment, and how does it navigate an environment with ice compared to not with ice? And that's a hard thing to do if you don't have video on there. So that's a really powerful advantage. Jen Tackerberry is going to come in later this week. She's going to, one of her big projects is looking at nursing behavior. She did a nice paper in Peer J looking at how like humpback whales, this is a video on a calf suckling from its mother. What she did is compare the kinematic signatures. We had a tag on both the calf and the mother and compare the kinematic signatures from these. Oh, one of the things I'm circling up on the top there, this is the very first deployment of a wireless tag from CATS. And you can see that the timestamp's like up in the corner, like there's just variations for this stuff that's happening all the different time. So this is work that Jen did to integrate the data sensors from the calf and the mom into looking at this nursing behavior. And the middle figure there is what Will was talking about. That's a track plot. And that's one of the things that Jen's going to talk about on Thursday is how do you use track plot to like take some information from these tags. Okay. This is a paper looking at how whales feed both slowly and how you can look at the kinematics of like looking at the overall environment, like what's going on in this whale's environment versus what happens when a whale feeds when it's traveling very quickly. So this is an animal traveling about 4 meters per second for almost a minute before it gets to its attended prey. It's really moving really quickly. And then it's moving quickly because it has this other context. It has these other dolphins chasing this animal around. And one of these things you can do is you can look at how this animal's behavior, how its skull and jaw motion, right, corresponds to the motion of its prey. So you can use these video tags to really look at the environment of what's going on and give context to what the signals are you're looking at. So this was a project where we like actually integrated the motion and behavior of the whale with some of the things like skull and jaw motion to predict what the prey are going to do. This is a paper where you're looking at the overall context. Like, well, why are whales feeding so much from our tags? Well, it's because in this situation, there's a lot of krill in the water and there's whales everywhere in this big supergroup environment. This is a project we did with Mdusi Kamela and Ken Finley in South Africa, looking at these large aggregations of humpback whales off the coast of South Africa. Just whales everywhere. And these are just really like, again, every time we put out a tag, we get something new. To show you one more video for today. Every time we put out a tag, we show something new. This is a fin whale off the coast of Monterey in Big Sur, California. And the tag gets slid to a very unusual location here, where you're kind of actually like, we call this the poop volcano, where you're kind of getting this whole just like, yeah, I'm sorry if you feel dirty from this. Finally, one thing to remember is that the tags are always recording. These are all just still shots from the tags on the boats of some of our different colleagues, and that gets us back to this being about the people in the audience. It gets us back to being all about us. So the first task we're going to do today in breakout rooms, we're going to send you guys to these breakout rooms. There's going to be about 6 people in each room. If you guys haven't used Zoom a lot before, what you'll see is this button on the bottom, this join breakout room button. So I'm going to create that here in a second. And then once you go into a breakout room, you'll just have 6 people, and that allows you to interact with people in your room. And that breakout room, once you go into that room, that'll change to this ask for help button. And you shouldn't need it this first time, but in general, that will help you. That if you're like working on some task and you're stuck and you're like, this isn't really working, we can't figure this out in our group, you can click on that button and then Will and I will see that, and one of us can come and join you in the room and try to help answer your questions as you're actually working on these tasks. So what we're going to ask you to do when I split you into these breakout rooms is one, just introduce yourselves to each other. Share your name, your lab office location, how you use biologging tags, what do you hope to get out of the workshop, just to kind of get a sense of like, okay, who else is in this workshop? What else are people doing? And then I'm going to send you this brief workshop assessment here. How do I get back to here? Oops.
Let's copy that to the now.
Yeah, I'm trying to go. Yeah. There we go. Chat. Come on. Chat. There he goes. Yeah, I don't see it. So, chats. There it is. So there's the link in the chat there. So you can use that. You can also, it's also in the day one materials. If you've already gotten to the Google Drive, there's a link in there. So what I'd like you guys to do is spend a little bit of time sharing your information about yourselves, and then fill out this brief pre-workshape self-assessment. And that'll just give us a sense of where are you now and where do we hope to get you toward the end of the workshop. And they're all simple questions, yes, no, with some basic information also from you, like what are some ways you learn best online? So it's 10:35 right now. We'll come back at 10:50 after I send you to your breakout rooms here. We'll come back at 10:50 for introduction from Nico. So we have about 13 minutes for this task here to introduce yourselves. I see from Ellen, I need to open up the form. So I will send out, I don't have permission to view the form. I gave you guys the wrong link. Stand by. I have it here. The one in the CATS workshop folder is correct. Try this one. All right, and now I will send you to the workshop links. Workshop rooms, breakout rooms, one assign. Boom. All right, so you should be being sent it out to there, and just accept join there, and that'll send you to your room. So spend about 10 minutes. At 10:50, I'll call you guys back. Still muted, Sherelle. I think you're still muted, Sherelle.
Hey guys, can you post the link in the chat? I'm
Boom.
here for breakout 7. Thanks.
Thanks, Camille. Sherelle, I think you're still muted.
Hey, Dave.
Hey. Sherelle.
Dude. Hello. Hey, Dave.
Hey.
Can you hear me?
Yeah.
Hi. Sorry. Will you send the link to the rooms again?
Yes. I unfortunately from the it's hard to copy from the announcement I make.
Oh.
But-
Yeah, you can't copy from the announcement, but I was gonna say the 2 chat links both just said you need permission to view this form.
This one too?
Yeah, both links you sent. Right now.
Aye. All right. Google's the best. I love Google. All right.
That's weird because I'm not having any permission issues.
Because
So
you're
it
at
must be
Stanford.
something
It's like a
funky.
Stanford thing.
Yeah, you gotta change it to allow anybody with a link, or not. Yeah, it just limits you to whatever institution you are.
I thought I had done that, but then apparently that was like the link to edit it. So let's try this again.
Mm.
I have a quick question for you.
Yeah.
Are you using Macs or PCs for this?
Almost everything is going to be PCs, but you can use Macs. Theoretically, you can use Macs. It's just nothing is tested in Macs. So that's the problem, is that nothing is necessarily tested. Don't know why I can't find this. All right, we'll have to change this workshop link, I guess. Might have to think some more about this. I see people starting to come back. I know we're looking for the link. Apparently it's still just, it's copy protected, the new link I sent. So let me see why that is. We'll just have to come back to that. I will, I'm gonna just let everyone know that apparently the link's not working. So we'll come back to that.
Dave, my whole group just came back into here to use the link.
Yeah, thanks. Apparently the link is still protected. So
Oh.
we'll have to come back to that. First snafu of the tournament. It's it'll be all right. We'll come back to it. It's expected. So we're gonna have some snafus. If that's the biggest one, then we're okay. We'll just get that out of the way early. We'll get that out of the way. So apparently there's a snafu with that. We'll start bringing people back. And then we'll push forward without knowing your pre-assessment links. So we'll come back to that if I can figure that out during the next video. We'll give about a minute for people to come back. Sherelle or anyone, were you guys able to at least, you guys were able to interact in the breakout rooms? Everything was going smoothly? Okay.
Yeah, no problems there. Said hello.
Great. Excellent. We'll use those same breakout rooms for later, and then eventually later on in the week, we can start setting it up so people can join whatever room they want. If you have specific colleagues you want to join with or whatever, we'll set that up as well. I see people coming back here. I'll give another 15 seconds here for people to show up. Okay. Thank you guys. Hopefully everyone was able to interact with a couple of people. Unfortunately, apparently the link was still write protected despite my best efforts. So if that's the biggest snafu we have, we're in good shape. We knew there were going to be some technical glitches. We'll come back to that. I'll work on that over the next thing as we move on, and we'll go back to breakout rooms in a little bit too with some other MATLAB activities.
We'll send it out as an early assessment instead of a pre-assessment.
Exactly. So what we're going to do next, I'm going to give a brief introduction, one more introduction from Peter Kraft, who's one of the two brains behind the CATS tags themselves. We've got Peter and Nico, and then after that, we'll start getting into some of the some content moderation. So this is going to be a introduction from Peter. He is able to join us virtually from the Alps. So we will see that going on here. Loads up. Nice.
Hello everyone, I'm Peter from Customized Animal Tracking Solutions, and we are here in the Alps, and there's a reason for that, because Nico and myself, who started CATS, are actually born here, and during that little introduction I will be in a few different places, I thought, and give you a little bit of a background information about how CATS got to be where we are and where we want to head. But for the time being, I want to say thank you for having us. A special thanks goes out to Dave and the Stanford group to organize that. That's also a first for us, so we are really happy to be part of that. And we are also very much looking forward to what comes over the next few years. And let's see how we go, and here are a few more informations from us, and I hope you'll enjoy the rest of this whole workshop. CATS has been established right here in the mountains about 7 years ago. Nico came over and asked me whether I would be happy to start a business with him, building tags, and I said, okay, why not? So we started off. And in the beginning it was just about small diaries, and it later became a little bit more advanced until we ended up with the CAT scan. Of course we did some GSM stuff and some other stuff as well, but the CAT scan became our flagship, and it was a very ambitious journey, to say the least. Our current setup and lineup of our products is more or less very diary heavy. So we have a mini diary, that's our smallest one, and that's been going for a few years now, which is very successful and really tiny but yet powerful. And then we had the HD CAT scan, which has now become the HD Mini, which is even smaller, and we will improve that with the new processing unit, making it even less power hungry. So we can make even smaller ones. That's for dolphins, for example, or even seals, turtles. That's the HD Mini, and we are also integrating right at the moment a full 96 kilohertz hydrophone if possible with it, but even a normal microphone if people just want some sound and don't want to use it scientifically. And then of course we have the 4K CAT scan, which is now our flagship. But it still has a few corners that we have to round and see how that works. But the firmware is almost there, and it's just a few weeks and hopefully maybe 1 or 2 months, and then we've got this under control as well. But this is of course quality-wise really the best that you can think of right now that we've got. Apart from that, of course, we have the normal diary, which is very powerful and new too now, with hydrophone or any other sensors if you don't need the video aspect to it. So there's basically really only the beacon missing that rounds the whole thing up, and the beacon really makes big progress right now. And it becomes very reliable for you to retrieve your unit. It is brilliant in giving you a rechargeable version, which is really nice, and it lasts for about 2 weeks with a lot of precise GPS positions, and that's really nice. And we also include and improve the portal. And Nico just the other day wrote something that we will be implementing, something that in the app you just get some option where you just hit it and then it shows you the track where you have to go in order to retrieve it. So almost the VHF is not even necessary anymore. But the beautiful thing is you've got even the VHF there that you can activate, and that lasts for many days after the beacon itself, the iridium-based satellite system, has died down because of power loss. The VHF will go on for days and is very powerful, and you can adjust at your own frequency, you can recharge it. So we are quite proud of that, and yet we are not quite finished with its development, but we are already quite far in, and it's very reliable at the moment as it is. In the past, CATS has focused on quite a few products, and it was mini diaries, GSMs, it was satellite-based stuff. But right now we are actually trying to restructure CATS a little bit and set the focus differently. Now we are focusing on Nico in Australia doing rather the back end. That means the customer service and especially the tag building, which he is really like incredibly good in, and much better than what we do here in Germany. So most of that will be done by him, and we will focus here in Germany really more or less only on the development of that stuff, and also the web stuff, the portal stuff for the beacons and everything. Having said that, over the past years we've also had a lot of different devices, whether it was GSM based or just mini diaries, or even some customer stuff we did especially for certain people, but that we will probably stop a lot and focus almost entirely on the CAT scan and its retrieval, which is our CATS beacon. And once we can perfect that, I think there is enough work for us there. And once we've done that over the coming year, I think we are really have developed a really nice device for you guys in order to be successful in the field and collect data. So here it is not really about telling you how CAT scan works or how the data is retrieved or being used. That's all what Dave and his friends will tell you about, and you guys are good in. We are here basically now just telling you a little bit about what will happen with CATS in the future right now, where our new focus lies, and also, as I already told you, about the history of CATS. So to keep this video short and not hold you up from what you're actually here for, I just wanted to say a huge big thank you also in the name of Nico, of course, in Australia. And it's been really great, the support that you've given us. And of course also a big thank you to the Goldbogen lab, and especially Dave and other people like Ari, for example. Everybody, it's been really, really great, and you showed so much patience towards us, because sometimes the devices just won't work sometimes, because we are working at the edge of what's possible for us as a small company. So every feedback and every understanding and every patience is hugely important for us, and we hope that our service and our basically support that we try to give 24/7 will make up for that. So again, thank you so much for having us here as well, and being able to provide you with some devices that will make you a better researcher and provide better data for your future research. Thank you very much.
Right on. Thank you, Peter. As Peter said, yeah, there's lots of things are always changing, and always using new and exciting. So we're always good chances to keep innovating and keep doing good things, and nothing is really static. One of the things I'll point out that right now is that we actually, if you're getting new CATS tags now, a lot of them are 4K integrated and have some really cool new features. A lot of the tools that we have right now are actually up only through 2K. We have done 4K stuff in the past, but the kind of the basic workflow stuff is only through 2K HD kind of cameras. So if you the idea is that this is a living document and a living workshop. So as we start getting 4K data in, and I start working on this and processing this 4K data, we will upgrade the scripts on the GitHub accordingly. So with that, we'll start moving on to some real data analysis. And Will is going to kind of lead us into that a little bit with some introduction to accelerometers and what are the tools on here. We're going to spend a day kind of thinking about what is this data that we're collecting and how does it work, and we'll go from there.
Awesome, cool. Yeah, that was a fun video. That's the first time I've seen that video too, so that was cool. Okay, hi everyone. So what we're going to be doing now, I just put a message in the chat a little while ago. This activity that we're going to just be doing quickly, this is just kind of setting you guys up to have a way to sort of understand inertial sensing units a little more, especially as Dave starts talking about it in about 15 minutes. So we're going to be working with a phone app called Sensor Kinetics, and it sounds like it might have some issues with new iPhones we're hearing, which is good to know. So if you have any issues, don't worry. This is more just like a fun tool for you to have to sort of, you know, help yourself understand this a little more. And this is something that we use pretty often to, or at least I use pretty often to figure out like, okay, what are the axis conventions? How should I move it in this direction to figure out how this works? So maybe, you know, just take like a minute or two to download that, and then we can start this rolling here. So I'm going to just share my screen here. And while we're going through, if anybody has any questions, either you can put them in the chat or just feel free to shout them out, because we're just going to be messing around with phones here for about 15 minutes. And again, if I'm not talking loud enough, I'm still getting used to this mask, so just let me know and I will yell louder. Okay, so starting here, we're at this exploration of IMU, inertial sensing unit sensors with sensor kinetics. So, like I said, let's take about maybe 60 seconds to download this this little app if you would like to. And what it's going to allow us to do is essentially look at the three main inertial sensing units, which are in the CATS tag. So those are the accelerometer, the magnetometer, and the gyroscope. And it'll allow us to see them in real time as we're sort of moving through. And actually, for those of you who have CATS tags or are working or are going to work with CATS tags, there is a way to do this with the CATS tag as well. It's called Live View. And we can get into that a little bit more tomorrow when we talk about calibration. But that's a really fun way that you can basically turn on the Wi-Fi of the tag and then turn on Live View and start to take your tag and really, you know, move it in all different directions and see what's actually going on and what the different axes are doing to the orientation of the tag. Okay, so if everybody who would like to download Sensor Kinetics has it, or is in the process of getting it, I'm just going to sort of move on to the accelerometer here. So when you open it up, you should see this screen. There's sort of three main sections. There's the accelerometer, magnetometer, and gyroscope again. So if you click on this little graph right here next to where it says accelerometer sensor, it'll take you forward into a screen here. And I can show you, for those of you who can maybe see my screen, you can see I'm now onto this next little spot here. And once you're on this accelerometer screen, you can do the same thing with the magnetometer or the gyroscope. If you hit the start button, it'll start to record data in each of the three cardinal axes of the tag, or in this case, the phone, right? So one direction would be straight through the phone, one would be up and down, and one would be side to side here. And so what we can see is if you put your phone directly on the table, you're going to have data going in these three axes in a very particular way. And so we have some questions here, just some quick questions, and if you want to come back and think about these later, they'll maybe be a little more time. I know we want to move through this little section quickly. But if you can think, you know, for an accelerometer, what are the maximum and minimum values, or what's the maximum positive and negative value in each axis? And I'll actually open that up to the floor if anybody has a guess. Feel free to just shout it out. Give about 15 seconds. Or put it in the chat.
-10 and -10.
10 and -10, yes. Excellent, thank you. Yes, so 10 and negative 10 is, 9.8 and negative 9.8, which relates to gravity. So the idea on the accelerometer is you have this small weight attached to a spring, and that you have 3 of them, one for each of the 3 cardinal axes. And as that spring gets, or as that weight gets pulled in one direction or the other, you get a force, pushing it or pulling it, which creates your value. And so if you are in the direction of gravity and that little weight is being pulled toward gravity, it's going to be pulled with a weight of, or a force of negative 9.8 newtons, which is the force of gravity. So your maximum value that you can get in any direction is gravity. And that's for orientation. Now, the thing about accelerometers is if you were to take your phone and now, let's say you take your phone and you push it really quickly in one direction or the other, or up or down, what you're going to see is you're going to get these big spikes in your data. And what's happening there is not just the orientation of gravity, you're also getting that weight being pushed. And that's actually called a specific acceleration. So you have these 2 different types of accelerations that you get together on the tag. And we actually use both of those. We use accelerometer orientation from gravity to determine the orientation of the animal, but we also use specific accelerations to determine things like when is the animal feeding, when is the animal fluking. We can use it to determine speed in some cases. Yeah, so one thing, and maybe we won't go through all of them right now, but how do you get an axis value to be 0? Well, as you can see, if you take your phone and just put it on the table, 2 of these axes are currently at 0, right? Because you have one axis that's being pulled by gravity, so that's negative 9.8. And then your other 2 axes are not being pulled by gravity in either direction. So those 2 axes should be 0, right? Because there's no force acting upon them. And then if you want to match those 3 figures that we have on the screen here, one of them would just be sitting on the table here. But if you want to find, let's say, that second figure, what might we want to do? And for those who can sort of see, I'll try to make this a little more visible here. So if we have it on the table, there's one of our axes, there's one of our figures. If we want to find our second figure, we can take it and we can turn it onto a different axis. So in this case, and I know it's a little hard to see, it's going to be sort of turned, but now we have a different axis facing and being pulled toward gravity, right? So now instead of our initial axis, which was the one going through the phone and out the front, that's now 0 because it's perpendicular to gravity. And we have our second axis that is now being pulled downward. If we want to find that third graph, what would we do? Now let's find that third axis. If we take that third axis and move it toward gravity, right? Now we're going to get our third graph. But one thing might happen if we're doing this. So if you look at it now, you see that 2 axes are 0 and one is negative 10. But in that graph, you see that you have axes that are 0 and one that's positive 10. So how would you change it from negative to positive? The way to do that would be to take your phone and flip it over, right? So now the axis is being pulled in the opposite direction. So now we're getting a value of positive 10. So that's how you can figure out not just sort of, bidirectionally, but you can really get orientation in any axis because you have that full range from positive to negative 10. So if I just sort of take my phone and move it around here for a little while, you can really see those values. Well, it's a little hard to see them there because it keeps moving, but if I was a whale and I was just swimming along like this, you'd really start to see that value, sort of that fluking value there. So again, this is a tool for you guys to have and to use whenever you need. Yeah. So that's the accelerometer. So next we're going to move on to the magnetometer. So for the magnetometer, again, so sort of go back out and then find your magnetometer, which should be, I think is usually the third one. And you click on that little graph again, it should pop up. And then if you hit start, right, so your data is now going again. And so a magnetometer in comparison to an accelerometer, which is like a small physical weight, which is really, getting pulled around by the forces of gravity. A magnetometer is a small magnet, which is attracted to the and changed by the magnetic field of Earth. So for the magnetometer, you can really use that not just to determine the pitch and roll of the animal, but the magnetometer is really necessary to determine the heading change of the animal, right? So if the pitch and roll are staying steady and the animal is only turning around on one axis, that would be really hard to get at with the accelerometer. But that is something that you can very easily get at with the magnetometer. So one thing to think about this, can you find the magnetic north of each of these three axes? So if you start with one axis, try to turn around. And one thing that's important to note here, magnetic north is not necessarily just going to be, turn toward the horizon or turn toward north on the horizon and there's your magnetic north. The thing about magnetic north is, since we're on a globe, a lot of times magnetic north will be down at an inclination angle through the horizon. So actually when I'm looking, what I'm trying to do is get two of these axes to be 0 and the other one to be my maximum or minimum value. And how to do that, I might have to turn it all the way and sort of find, so that is approximately where it is for me, if you guys can see my screen. My phone is tilted all the way down toward this magnetic north, which is not sort of just at the horizon here. I have to tilt it all the way. And so that's for one axis. But if you want to find magnetic north with the other axis, what do you have to do? You have to now turn your phone. Now, so instead of looking at it with this axis, you're now looking at it with the new axis. And then again, try to find that magnetic north point where two axes line up at 0 and the other one is negative or positive. And then do it with the third axis. And that might be that you're sort of looking directly at your phone, right? And so a lot of these are going to come into play when we get to the calibration stages, especially with the magnetometer. You're going to have to go outside. If you have a tag and you're following along or anything like that, we would recommend that you go outside away from any sort of magnetic interference, and then you can really get out there and point your tag toward magnetic north, and then start doing some of your small calibration steps that we'll get into later. And then very quickly, we'll go through the third one, which is the gyroscope here. And so the gyroscope, actually, if you were to open up your gyroscope and then click start, what you're going to see is that all three axes are zeroed to begin with, right? And so a gyroscope is measuring not the orientation at a given time. The gyroscope is measuring the rate of rotational change. And again, we have three axes of our rotation and three axes of our gyroscope. So how do we get positive and negative values? Well, if you take your phone and you leave it on the table here, and then you take your phone and you flip it over, and then you flip it over again, what you're going to see is you're going to get these spikes along one axis, right? So if you take it and you essentially rotate it, depending on how fast you rotate it, you're going to get values in one of your axes, whichever axis is being rotated at that given time. So if you take it and you rotate it along a different axis, so if I just spin my phone like this, you're going to see I'm going to get some data in that red axis. And the same if I do it along the third axis of the phone. should be this. So how do you get these three figures to line up? All you need to do is essentially take your phone and rotate it along your three different axes. And that's really helpful with the tag. If you have a lot of rotation at a given time, or you're trying to figure out the rotational rate of the tag over time, you can use the gyroscopes to help you figure that out. And so I'm gonna turn it over to Dave here. But I want you guys to, really think of this as a tool that you can use as you're trying to figure out axis conventions to figure out, not just, okay, what are the three axes of my phone or my tag, but really, which direction is the positive axis direction and which is the negative axis direction for all three of these X, Y, Z coordinate planes. Yeah, and with that, I'll turn it over to Dave.
Thanks, Will. Yeah, I think one of the things we'll do a lot in this workshop is kind of jump back and forth between kind of the conceptual aspects and then the hardcore like coding aspects. And because I think, and some of you guys might already be really good at the conceptual aspects and kind of know all this stuff already. And some of you guys might be getting a lot out of this part. And it's not that you have to like be an expert at all of these parts, but the more you can understand kind of what's going on within the tag itself, the easier it will be to like troubleshoot later on or understand why we're making the decisions that we're doing. So thanks for kind of going through all of these pieces. I want to get into some of the axis convention stuff, but I did get the link to work, I think. So we're going to send it into the chat here to everybody, not just to Taylor, who I've been chatting with on the side, but there's the link to everyone. So go ahead and try that link. Hopefully you can go there, and I'd love to get this pre-assessment for you. It should just take a couple of literally 2 minutes to go through and just say yes, no, yes, no, yes, no, etc. And we'll do that as I get this next one here set up. And let me know if there's any problems, but I see people working, so that should be the right thing going on. Not rushing to here. We're just getting the next set up here, but no rush. Take another 2 minutes to. We'll start again at 11:20 to go through the next step. So what we do, this is just like CATS tags. You have a problem, something goes wrong, then you fix it, and then it works from then on out. So now we're Google Form pros. This is what we do. This is what I do. So thanks, guys. We're back to being pretty much right on time with the workshop flow today. We're going to get into an activity here as you guys are finishing up that survey. We're getting into activity here with axis conventions. It's one of the things we need to be able to think about is understanding our tags, right? Like understanding what is actually this data coming out of there, and how does my tag that you have might differ from the tags that Will and I use, or that your colleague uses, or that they use the D tags. Like what are the differences there? And when I first started doing this data analysis, and I was just kind of given some data, and I didn't really have the context for it, it was challenging for me to kind of think about like, well, what does this data mean? And so I always like to start when we do these kinds of ideas and workshops with, well, what is going on? What are our axes? What is everything actually measuring? So that's where we're at right now. We're going to kind of get into this idea here a little bit with a basic essential question of, well, first of all, I'll just pause. Does anyone just give me a holler or chat or something if anyone needs more time for the forum? I can pause if anyone needs more time. Awesome. Thank you guys for playing along. Okay, so essentially here, where the idea is, we're getting to this essential question of like, what are the primary sensors used by these tags, and how do they work in CATS tags? So we're going to start right now examining data in MATLAB. So if you don't have a MATLAB tab open, worth trying to get that started up. We'll send you to breakout rooms to actually do some of these activities. But so if you don't have MATLAB, you can maybe follow along with someone else, and I'll show you some examples as well. I know one of the difficult things of doing this virtually is the idea of having to switch multiple softwares, and like whether your computer can handle like MATLAB and Zoom and processing a video all at the same time. So we'll just kind of keep doing it, and we'll keep pushing it, but we understand that like, yeah, it might not go as smoothly as we want. And I know that I have 3 screens going on right here. So I know you probably do too. So we'll have to kind of be patient with each other as we try to figure all these things out. But we'll keep working through it. So thank you guys so far. Okay, so this is a virtual whale. This is when I talk about axis conventions, this is what I'm talking about here, where you have an x-axis, a y-axis, is a z-axis, and in your data set, that's going to come down as 3 columns of data. Usually the first axis is x, second column is y, second column is z, and how those relate to your tag can vary from tag to tag and from system to system. So we'll get into why we use this system with CATS tags, or why I have set it up to use this system in CATS tags in a little bit, but I just want to start with this assumption of, okay, this is what we're using. And what that means is that, as Will talked about, gravity is that main axis. Gravity, we use gravity in relation to g. So in general, we talk about that accelerometer axis is always measuring gravity. It's measuring a +1 g going in the up direction. Some tags have started to switch to do that all in meters per second. It's really easy to meter per second squared. Let's be precise. We're scientists. Meters per second squared. And so it's easy to convert those. If you need to convert those back and forth, you multiply by 9.81. We use g as 1 just as a standard measurement of acceleration. It's one of those conventions that people use. We've kind of maintained that convention from older tags. You can use meters per second squared if you'd like that, or you can convert between them if you want to think in that way. For a lot of purposes, it makes sense to use meters per second squared. It also can make sense to use 1, especially for the tag processing steps. It can make sense to do it as 1. Okay, so why is gravity 1 in the up direction? Gravity goes down. So let's think about that for a second. What's going on? Why is gravity +1 if it's facing up? Well, the answer to that is the one way, and if you're playing around with your sensor connects there, the one way to get all the accelerometer axes is 0, as Will talked about, is if you throw your phone up in the air or drop it from something really high. In that case, then there's no acceleration acting on it. It's in free fall. There's no acceleration acting on it. As soon as that phone hits the floor or rests on the table, then there is an acceleration now going in the up direction, kind of in resistance to that free fall. That is what it's measuring. And that is why you have a +1 there. The other way to think about it is think about that actual sensor. Will showed that slide of the, yeah, look at Will throwing his phone up in the air. You showed that slide of the actual spring within the accelerometer pushing against the sensor, right? Like you can think about that, like if you're in a car and the car's accelerating, you're getting pushed in the opposite direction of the way that the acceleration is going. So the same thing is happening here. That little sensor, that little force sensor is being pushed down by gravity in the accelerometer, and that what creates the +1 in the opposite direction. So functionally, the result of that is that in our tags, when we talk about a whale sitting in resting position, this is the ideal whale, as physicists like to talk about, right? It's a whale just kind of sitting at the surface, not doing anything, sitting at the surface. In that situation, the acceleration in the z-axis is -1 in our axis conventions, and 0 everywhere on the x and the y. There's no acceleration in the x and the y in this case, just a -1 in the z. So that would be just like a perfect flat negative z, x and y are 0, -1 z. So far, so good. I don't see any questions popping up in the chat. We're going to keep pushing forward. Feel free to jump in or just unmute yourself and jump in if you have a question about that as well, if you're thinking about these. Okay, so now you got your whale. Now your whale moves on all the directions. So now in this situation, my whale is moving straight up, ascending to the surface. In this situation, given our axis conventions, the gravity is that positive direction. So we would be having a +1 on the x-axis and nothing in the y and the z plane. So this is starting to get at how we actually calculate orientation from the accelerometers. If you have a full set of 1 in the x direction and nothing in the y or z, we say that our pitch of that animal is 90 degrees. That animal is 90 degrees up. So we're going to get at how do we calculate that. I'm just going to give it to you guys today. So it's a little trigonometry, but it's fun. So we'll get at that idea here. So we have, if our whale's sitting normal and flat, there's no acceleration in the x-axis. If it's going up into the air, there's some acceleration in the x-axis. If it's going straight up, that acceleration is 1. If it's flat, it's 0. If it's in between, it's somewhere in between. And so the way you can calculate that is by basically using your high school trigonometry, your SOHCAHTOA ideas. You can move that little AX diagram, how much acceleration is measured in the x-axis, to measure that pitch. You can create that similar arrow up there on the top side, and then you see that right triangle that we're all used to looking at. And so then if you recognize that the pitch angle is the same as this angle in there, you can just set up a sine equation that measures your pitch. And your pitch angle is then going to be the arc sine of AX, that opposite side, over G, that hypotenuse. Now, because there's often acceleration in other directions, there's dynamic acceleration, static acceleration, we don't just assume G is 1 at all times when we're measuring pitch. We actually look at the magnitude of that hypotenuse. And so the magnitude of that hypotenuse is the Pythagorean theorem in three dimensions. So it's the ax squared, that all three axes, a square root of x squared plus y squared plus z squared. It's just our Pythagorean theorem. So this is the formula we use to calculate pitch. Now, you don't have to know this formula or memorize this formula or anything to use CATS tags, but when you see it, if you're looking through the code, this is where pitch is actually calculated from. It's basically the AX acceleration at any given point divided by the magnitude, the hypotenuse, that hypotenuse. So it's just that the pitch is just this angle. Also give you the formula for roll, which comes from a similar idea. You can I'll leave that proof to the user, the derivation of the user. But the roll is the similar trigonometric identity. It's just the arc tangent, inverse tangent of the y-axis over the z-axis. So you have those three axes, and that all comes from our orientation of our tags here. Okay, so to start exploring with data, we've got a task for you guys. We're going to have an activity here where we're going to load you into breakout rooms. I am going to bust out of this and show you some MATLAB here. You can use a lot of different versions of MATLAB. Basically, we've tested all of this stuff from everything from 2014 up through 2020. This is a 2019 version. Those of you guys have explored the website, hopefully by now. In the website, there is the link to on the code and tutorial pages. There's the link to the Google Drive. So there's the GitHub repository with all of the code that we're going to be using starting this afternoon, starting in about an hour. And there's this Google Drive, which has a lot of data and things in there. Now, this example data folder is the main processing script. That's basically a whole deployment of data from the Antarctic that we're going to be using and trying to run through as an example to give you, to run through this whole PRH making process. That is a big folder, so it might take some time to download that folder. So if you don't have that downloaded yet, you might start that either now if you can or after the workshop. We'll start doing some of the audio stuff next under Will's next section here. But today, right now, for this first activity, we're going to go into this workshop materials in day 1. In your day 1 data files, there's a couple of little scripts here. So I'm going to just switch over to my Google Drive version. So once you download that, you have this part 3 here. This is what we're going to use right now. We're going to use this part 3. And you can either load that, you can either go to the open button up here and open it and navigate to it and open it, or you can just slide it right into the editor here. And then you have it in your part 3 here. And basically what you're going to do is take this and take this part 3 example data, which you're also going to load the same way. You can either open it up here, or you can just slide it into your workspace over here. And it's going to have 3 variables in here. AW, which you can double click on to see. It's going to open up. So that's my acceleration of my whale. Then 3 axes, you have an X, the X, the Y, and the Z in our 3 different axis orientations, our X, our Y, and our Z. So those are our 3 columns of data there. This is a short snippet of data from a deployment on a whale Then you have the other piece of information that we're going to be coming back to a lot and introducing as different variables is P, which stands for pressure, which is basically our depth. And we'll alternately use either depth or pressure. They're both essentially depth in meters of the animal. And then DN is a date number. It's the MATLAB version of keeping track of time. Time is, it's hard to keep track of what day of the week and what day of the month and how do you make these things linear and whatever. So the way MATLAB does it is it keeps track of the days since the year zero that this thing is. And these are all, each one of these individual things is like a very long string of numbers. So it's 736,071 days since the year zero. Then this is a fraction of a day. This 0.642, et cetera, is a time. That's how it keeps track of time. So all of our data ends up keeping track of time for this deployment as this date number, sequential date numbers. And you can, we'll get over some things to do, but just as a brief example, one thing you can do is you can calculate you can have it convert that into something that makes sense for us. So you can see date string of the first DN there, and it gives you a date and a time. You can tell the date string of the DN end, that'll give you the time at the end of the deployment. So this is a 1 hour and 35-minute deployment on 17th of April, 2015. You can do a bunch of different formatting things in here too. You can have it give you the time in minutes, seconds, and FFF, which is fractions of a second. So you can really get precise in these date numbers. And then as you want to learn about these in MATLAB, you can always do like help or doc date string, or help or doc whatever function you want. And as new MATLAB users, that always come back to it. So like, we'll give you some tools, but if you want to learn more about it, like, well, what are some different formats I can use? You can read this whole section in here. MATLAB is pretty well documented like that. Okay, so the task I'm going to send you guys to breakout rooms for is to load this data, try to run all of these different lines. And if you're new to MATLAB, you might want to run them line by line, either by copying them down into the window down here, or you can also press F9. F9 will run that piece and bring up that figure. So you can kind of get a sense of what each line does. You're not going to have to do much of this like coding, like basic level coding to run the PRH stuff, but this is like basic scripts that are good to get a sense of. And for those of you guys who are more advanced, who use MATLAB all the time, there's still thoughts in here. Like once you do this, there's questions in here. I want you to actually tell me what this animal is doing by looking at the data. If you can, talk with your groups about doing this. So right now I'm going to split you guys up into breakout rooms and have you guys try to work through this. It'll take about 15 minutes to work through this. We'll bring you guys back at 11:45 with some discussion, with some ideas of what do you think this animal on this deployment is doing. Any questions about what to do before I send you out there? Sweet. I'm going to open all the rooms and send you guys to your rooms. And then if you need help, tick that ask help button and Will or I will come join you guys. You should just get a link that says, okay, join in your room. Yeah. Oh, and there's a new people who are unsigned. So I will assign you guys new people to some rooms. Assign to, just choosing rooms that have fewer people. Introduce yourselves if you've never been there before. Bam. Right on. Well, I'm going to stop the recording for now while I forgot to do that recording here. Thanks. Awesome. So you guys should have been able to make a plot like this. I think I see everyone back now. Let me, before I get started. Yeah, okay. Navigate in the tabs. So you should have seen made a plot like this if you have an older version of MATLAB, or like this if you have a newer version of MATLAB, depending on your color schemes that you chose. MATLAB keeps changing slightly over time, and it's not at all frustrating, I promise. It actually is very frustrating. But there are different tools to use. So like if you have an older version of MATLAB, your zoom tool is up here. And because we link the axis in that code, you can zoom in and then see all these things kind of stay together and linked up in the axis over there. In the newer versions of MATLAB, it is the zoom function is over here, not the zoom like what you're watching, but the zoom like zoom in to the screen, zoom to. So then it has the same purpose. It has the same functionality where you can zoom in and out of those things. The other hint I wanted to show people as you're running these codes, because we'll do this a lot. So the main MATLAB script, which we'll get to a little bit later today, is this main cats PRH tool. That's all divided into these cells the same way this is. This double % sign makes cells. And so if you wanted to just run all this code together at once, which we sometimes will do, and we'll have it set up to do that so you don't have to run line by line, you can either do this run section here, this run section script up on the little button on the top there, or you can also press Control Enter. We'll also run that whole script and make that plot. Just by pressing Control Enter, we'll run that whole thing. So those are your hints for your MATLAB hints of the day to do those. So you should have gotten a plot like that. I'm gonna switch back to this plot here. F5, shift F5, and switch my screen again. And go back, forward. Oh, where is it? Okay. So you should have a plot like this. Where no matter where you zoomed in, you had similar kinds of things going on here. Before I kind of get into like what I'm interpreting this data, is anyone willing to be brave enough to jump up in front of the big group here and talk about what your group talked about in terms of what do you think is going on with this data? How can you interpret both the accelerometer data on the top graph like that, the XYZ, or the depth and the pitch and roll there? Is anyone willing to share what their groups discussed? I'm sorry I didn't warn you ahead of time that you might have to do that, but is anyone willing to jump in and talk about what you found?
I can take it off your hands, Dave.
Nice. Get in there, Carrie.
We were thinking that it's a typical blue whale lunge feeding, so it's rolling at the bottom of its dives. The question that we came up with, though, is roll doesn't seem to be, you can't tell right or left. And so we're missing something, I'm guessing, up in the X, Y, or the Z to note, because since the roll, that red line in the bottom plot, just goes to 0 and then pops assumably up to 180. How do you know when is that 0 crossing? It's like center line crossing. And then how do you know if it's going right or left?
Great, good questions all there. The right-left ambiguity is exactly what we'll talk about next. So hold on to that question. That's a great question. And then exactly, this idea that, so the Z-axis here that Carrie is queuing off of, here's at -1. This is a whale pretty much in regular position, right? Like it's just it's oriented correctly. Like X and Y are about zero acceleration. Z is at -1. So you have that whale kind of sitting in normal position. Something starts to change here. The Z-axis not only goes up to 0, but then goes cross 0 and comes back around. So that whale is actually rolling more than 90 degrees, not quite up to 180. 180 would be all the way up to where that Z is totally upside down, up to 1. And you see that here on the roll axis when you actually calculate roll. The roll does not get all the way up to 180. It gets up to 120 or so. So we'll get to that left-right ambiguity here in a second. So Carrie's group thought blue whale lunge feeding. Excellent. We got rolling. We got group behavior going on here. Any other interpretations we want to throw into there? Any other group want to jump in and say, did they talk about the same thing or different thing, or confirm? Do they have the same interpretations as Carrie or Carrie's group, or anything else? Or different interpretations?
Similar, but the depth of the guy goes down to 3 meters. I mean, I'm not a whale guy, but I'm pretty sure. I don't know that. I think whales go deeper than that. So unless that's an error on the axis. So we decided it wasn't lunge feeding specifically, but maybe just being lazy at the surface and rolling around, or whatever whales do at the surface.
Whatever whales do. All right, cool. Taylor's group just says, looking at the depth axis and say like, yeah, 2 meters is actually, that's pretty shallow. So it's just at the surface. Anyone else? Any other interpretations from any other groups?
Hey, Dave, it's Arena.
Hi, Arena.
Hey, so we noticed that as well. And something that we talked about was maybe a gray whale. because I think they feed benthically and pretty shallowly.
Oh, interesting. No, switching species. We're getting off. I know I love me some blue whales and humpback whales, but now we're getting into the way to bring out the UCSC gray whale idea, because we have a lot of gray whales coming around through that area. Okay, so now we have a gray whale thought. Anything else? Any other groups want to throw in some information there? All right, indeed, that's a good one to end on, because indeed this data is from a gray whale. This is a picture of a gray whale feeding. So that those dives that were to 2 meters, those dives, that's also bottom feeding. That's literally a 2-meter dive to the bottom where the animal is rolling around in this shallow water. So this is a flipper up here. This is a fluke back here. So this is an animal rolled onto its right side. And we'll talk about how we know that from the accelerometer as well. Roll onto its right side. So we're looking at the underside of the whale in essentially 2 meters of water, where that animal is at the bottom, where it's so shallow that it's, even though it's feeding along the bottom, its flippers and flukes are sticking up out of the water. So this is a tidal flat area in coastal Washington, near Everett, where the whales kind of wait till the tide to come up, and then they feed on these ghost shrimp areas in there. So it's a really cool animals, pretty cool data. This is some pictures of these gray whales. There's one with a tag on it there. And you can see this mud trail that it leaves behind it. So that whale is actually doing this for an extended period of time, where it's kind of digging this pit along the bottom. And you can see that mud plume as it's feeding along in that shallow water area right there. And so this is a track plot of that an animal doing this thing, basically like diving to 2 meters, rolling and digging in the surface, doing that thing again, and moving along in there. We'll talk about like making pseudo tracks and stuff here, and to what degree this is representation of forward motion or stopped motion. It's always represented as forward motion in this track plot, but you can kind of examine that here. So I think this is pretty funny. You can see not only that roll to 90 degrees, but also that pitch. I think I go back if I can to our plots. So you can see not only is that rolling to 90 degrees or bigger, as Carrie pointed out, but also that pitch angle kind of changes and goes down a little bit to about 30 degrees or 20 to 20 degrees. So that animal's actually angling itself down as well during those time periods. And so just getting used to thinking about like, okay, well, how do we interpret both this acceleration and this pitch and roll? Those are kind of useful things. Once you don't necessarily, when you're doing analysis, have to deal with these raw acceleration data, but it's useful to be able to kind of like, sanity check all your work to make sure see what's actually going on here. Okay, so let's get back to thinking about axis convention. Yeah, question, go ahead.
Can you verify that depth axis is always in meters out of your MATLAB code base? Because we were getting it in 1 to -1, and we're thinking, oh, that's G. Oh, and it just could have been that we were at a different scale, because there's not labels on the plots, and depth I was kind of going between is this meter? It's not decibars, obviously, which is what I'm used to in the Akusons. But apparently you've backed out meters of this already.
Yeah, what we should always have here is, so the 1 and -1 should have been this accelerometer, and then the depth should have been P, that P value is in pressure. So it's depth in meters. Yes, so it should always be the way we're coming out of these is depth in meters. And I'll show you guys later on, that's a good reminder. I'll show you the text file that we have that kind of lists the definitions of every variable that we're using. So you can always refer back to that as well. So yes, excellent question. This should be depth in meters as we come out of this. And part of what we'll do tomorrow is talk about calibrating that pressure sensor coming in so that you get out depth in meters. So that's a great lead into that. Those are all excellent things. Okay, so great, that was awesome. Thanks guys for jumping into there. So let's get back to thinking about our axis conventions. I just want to give you a little bit of history of like why we choose this axis conventions. It's kind of a little funny here, especially when it comes down to like, part of it is when you're making a manufacturer, when Nico or Peter are getting involved, you can take this data board that has an accelerometer and a magnetometer and a gyroscope on it, and you can put it into the tag in any orientation you want. So like what's actually getting reported by the tag might not be the conventions that you actually see here. So one of the things we'll think about here in just a second is how can you tell what is being reported in your tag once you get your tag off the shelf, like what's actually the right thing. And so we try to have this same, we always want to convert everything to our same conventions, to use data in the same way at all times with this XYZ axis conventions. But yeah, it doesn't always start that way, because you can have these data boards in any way, come in any kinds of ways. Okay, so I've been using this like hand thing a lot. this is exactly kind of what I'm talking about here. We're representing the x-axis with my index finger, the y-axis with my middle finger, and the z-axis with my thumb. This is what we call a right-handed orientation axis convention, because right-handed represents that XYZ orientation. I want to talk a little bit about why I chose this, because it is a convention. It is just a convention, and not all tags use the same convention, and you could set up your tags differently. This is one of the things that confused me at first early on, is that different tags might have different things, and it's not always clear. D tags, for instance, for those of you guys who are used to looking at D tag data, often use a left-handed orientation where the z-axis is positive, and the x and the y are the same way. Now, the reason that we set up the CATS tags this way with that right-handed Z down negative has to do with the rotations. Because I want so rotation, when we talk about pitch and roll and heading, and when Carrie's talking about, okay, does it go to the right or to the left? One of my struggles as a scientist is memorization. I'm not a very good memorizer. I lose track of what things are. So I often go back to first principles. And so the fewer things I have to just remember just because that's the convention, the better. So I was a math teacher. I think about rotations this way as a counterclockwise rotation from the axis of interest. So this main 0 degree axis right here, I think about rotations as a counterclockwise rotation. It's a positive rotation is counterclockwise. So this would be a 135 degree. Here's a 90 degree rotation. Here's a 210. Here's 300 degrees all the way around. And then negative goes the other way. So negative rotations are go back to the right. That might have been the way you learned it in school. It might not be, but because again, it's just an arbitrary convention. But it's how I think about it. It's the one convention I try to memorize is rotations go counterclockwise. Okay, so how does that relate to, and so then, sorry, so I just want to add in that then plays a difference, how those orientations come together plays a difference in how you set up your rotation matrices in the code. And so that's why, like, at a certain level, it's important to remember those. Once you can kind of remember it, you don't have to deal with these anymore. But when you're trying to set up these matrices, knowing what your conventions are is really critical. Okay, so how does that relate in 3 dimensions? Well, to rotate in 3 dimensions, you have to think about that third axis coming out of the page. And so it's a counterclockwise rotation around that third axis coming out of the page towards you. So it's still counterclockwise if you're looking down that third axis. And so that's why you get these rotations this way. And so then when we want to set up our axis conventions, if one of the things that we want is pitch to be positive when that whale is ascending and negative when it's descending, then in order for my pitch to be positive, I want that rotation to be counterclockwise this way. So one of the advantages of this orientation is that pitch is positive up when it's rotating up counterclockwise in that direction. One of the confusing one is that the other thing that I want is the heading of the animal to be like a compass, so that you can say, like, if the animal's going at 60 degrees, or if it's going at 90 degrees, that's east. If it's going at 180 degrees, that's south. If it's going at 270 degrees, that's west. So I wanted to set it up that way. Well, a compass is set up as a clockwise rotation. So in order to make that counterclockwise rotation work mathematically and in my head, another benefit of this rotation is like that, because if you're looking up at the bottom of the tag with that z-axis coming down at you, it's a counterclockwise rotation that matches from the top, that clockwise compass rotation. So that's why we set up the tag this way. Another advantage of this is that that's how actually a lot of other tags do it. A lot of tags come out. One of the things that we'll see in our tags that we use, most of the CATS tags off the shelf actually come in this orientation. So you don't have to do a lot of converting back and forth. So there's some reasons for this besides just counterclockwise rotation, but that's why I do it. Now, just to talk about one of the implications for that, if you are used to using D tags, one of the differences, right, is that the z-axis and the roll have opposite signs. It gets back to Carrie's question from earlier, is roll positive or negative? In CATS tag, the positive roll is to the right, versus in D tag, the negative roll is to the right, positive roll is to the left. So if you have the same data, but we're looking at a D tag axis convention versus a CATS tag axis convention, you get slightly different data. Here's that same, we were using the CATS tag data, here's that same data, but visualized as a D tag, where the Z axis is now positive when that animal is resting at the surface instead of negative in our conventions. And the roll is to the opposite direction. So this is a roll to the right. The animal's still rolling to the right no matter what our conventions are. But in a D tag, that appears as a negative value, and in a CATS tag, that appears as a positive value. I'm sorry if that's confusing. The only way I ever remember it is to come back and just think about it always from first principles. Our axis conventions is right-handed this way, counterclockwise rotations around the axes. We also describe this in this document that I'll show you here in a second as well. Actually, I'll just show it to you right now. In your workshop materials, I'll just show you this. One of the things we do is, oops, in the example data, we've kind of set up this folder with the example data, kind of everything that you would normally see. Oh, I actually don't see it. I take it back. Let's go back to workshop materials. Okay, I don't see it in here. Let me open one up. Cats tools. This cats variable names, which I will put into the GitHub. Oh, it's in the GitHub. That's where it is. It's in the GitHub link. Sorry, it's not in the workshop materials. It's in the GitHub link. But this has the definitions of everything in here. And you don't have to go over all this now, but I want you to know where it is. It's in the GitHub link with all of the main tool codes. And it just has a description of all of those things. So if you ever get confused, you can say like, okay, pitch of the whale is this, the roll of the whale is what do these variables actually mean? And I'll add in here, actually, I can add in here that it's positives to the right. I should add that in there. But then you have things like, okay, well, P is pressure, depth in meters. And what is P track? Well, it's a pseudo track of the whale in meters and XYZ coordinates. So you have all these variables, which is what we're going to create over the next few days. And just wanted you to know like what those things represent. So that's going to be, can be a good reference for you as you come back to these things. Okay, so back to axis conventions. Back to axis conventions. Swap this back up. Okay, so like I said, so this is the axis conventions tool in the CATS utilities. So once you've gotten the GitHub down, you can get this axis conventions tools. It's in one of the scripts in the subscripts there. You can always find all these tools. You don't have to always navigate them in the folder. You can, if you know what you're looking for, you can just say like open axis conventions and it'll pop this guy up. And this is something you probably don't ever have to set this if your kind of convention already exists. But if you have a new tag with funny axis conventions, you might have to add in your own code in here that tells you what the axis conventions are for your tag. So like I said, most of the time, this XYZ, this just means that like the tag comes out with the accelerometer, the AX, the magnetometer, the M, and the gyroscope, the G, all come out in the right orientations in the tag, in this wireless tag that we're used to dealing with from CATS. But it doesn't always have to be that way, and it's not always that way. Some of the first tags we got, this platypus style tag, had some funny axis conventions, were different. So instead of like having our XYZ this way, the tag came out with Y and Z reversed in the accelerometer. And the magnetometer was even rotated from that. The magnetometer had this, that was in a totally different orientation with the Z axis coming out the side and the X axis coming out behind and the Y axis coming out the top. It's still, you can still arrange your fingers to kind of match that, but it's not the way we want it to be. And so in order to convert those, and the way you test that is using like the software that Will showed, or in your live view of your CATS tags, you can actually look at what is the data stream coming out of each one. So when Will was talking about like, okay, move your phone up so that you get the X-axis there, if you rotate your phone up and it's the Z-axis that is now facing, if you rotate your tag up, the front of the tag is up and the Z-axis is now facing getting +1, you know that that's actually being reported in the X-axis. So that's part of what you can do is try to figure out. One of the exercises we could do is take your tag and try to see if you can, or your phone, and try to recreate what your axis conventions of your phone are. Because I'll bet it does not match our typical one like this. And so can you create an iPhone style axis convention here that tells you, okay, so what column actually is? So is the first column Y, is the first column X, is the first column Z, like what is that actually doing? We won't have you do that because everyone's got different phones, so it's hard to like even have a standard here, but it's something worth thinking about. And if you get stuck on that down the line, if you have a tag that does not looks like it's not X, Y, or Z in that order, then we can talk about how to add that into this code area. As Will said, we're looking at the accelerometer. That it's just using gravity. For the magnetometer, it's looking at that true north value. Yeah, Julia.
So Dave, thanks for noticing. Do you have to load anything like when you're actually deploying the tag? And I might be going a little bit further here than what you want, but like D tags, they sometimes have this identity crisis, right? That you have to reload the application. Do you have a similar thing with the CATS tags, or do you do all that post processing?
So with the CATS tag, good question. So the CATS tag, we do a lot of both pre and post processing. So what Will's going to talk about tomorrow a lot is the actual calibration part we do ahead of time to determine the access conventions and get your kind of your information ahead of time that you need. Then you can just deploy the tag. And as long as you kind of set your settings the same every time you deploy the tag, and then afterwards we'll apply the calibration. So you don't have to do too much messing with the UI. The UI is always the same. You have data, you know, even if you do the calibration stuff after the tag comes back, it's okay. That's bad practice because if you lose the tag or the second deployment or whatever, but you can do those things. So yeah, it's not, you don't have to do too much like applying a thing during the deployment.
Great, thank you.
Question?
Yes, it does. Thank you.
Taylor?
Can I ask a quick question? Yeah, one, with, you know, I guess the idea is these are going on perfectly in each, on each plane, right? So what about the calibration? You have to do post-processing. Maybe you're going to get into that, but like, you know, when you're, if like for me, sometimes I put the tag on upside down because this is the way the shark's coming in. So what about dealing with that? You know, your data are really clean, X, Y, and Z on the, you know, on your example, but what about when it's not clean on a real animal?
Yeah, that's a great question. So Taylor's talking about what happens if your data is not oriented correctly on the whale or on the animal. Let's be inclusive here. So it could be a shark, for instance. If it's on the, so if your tag's oriented incorrectly, so this tag is actually on the whale crooked here that you can see. That we will get into that. The short answer is we'll do that all on Wednesday. And that's the difference between tag frame and animal frame of the axis, where we'll do a rotation. We'll talk about some MATLAB scripts we have to actually do a rotation of tag frame into animal frame. So everything is oriented. And so the data I gave you guys in that last example there was AW, which is the whale frame data. So that was already calibrated into the animal's frame, even though the tag itself went on in this funny orientation. So we will talk about that.
Dave, I think Leah has a question, and then we have one question in the chat.
Great.
Hoffman. So yours was first, if you want to go for it.
Yeah, can I answer or ask mine? So really quickly, because I've never looked at this tag data this closely, can you just explain to me what the units of time are on the x-axis?
Yes, great question.
Or what's going on?
Yeah, good question. So there's that DN variable I showed you before. That is that's keeping track of the timestamp of every data point. So if your data is sampled at 400 hertz, it's every 400th of a second. If it's sampled at 10 hertz, it's every 10th of a second. This right here, this was lazy plotting, where it's just samples. So however long your data is, this is just the number of samples since you started your data set. So this data was at 10 hertz. So this is 22,000 here and 22,500. So this is 500 samples, so 50 seconds between this data point and this data point here. So eventually we'll get into plotting better with time, but in this case, it's just samples. Good question. And then what was the chat question?
Question in the chat, are the XYZ on the Sensor Kinetics app the same as our XYZ? So Dave, I think you mentioned that, not all phones are going to be standard. So I think the idea is you can use the Sensor Kinetics app to figure out what the axis conventions are. So it should, I think if you turn on the legend in the Sensor Kinetics app, it'll tell you which of those three lines are which of the three axes. So you can use that to figure out which axis you're actually playing with at any given time. But as to whether or not they're the same as the ones on the tag, I'm not sure. Yeah, I'm not sure, because it'll be a little bit different depending on your phone possibly, and it'll be a little bit different depending on which tag you're using.
Yeah, and they're almost definitely not XYZ. Like it can be oriented, and the X and the Y I think are swapped from what I would think about it as usually. So it's worth playing with though and figuring that out on your own as an exercise. Okay, we're gonna move on here because we want to be able to kind of do a couple more activities before we have Ari, welcome Ari here at 12:45. So I wanted to just show introduce what Will's going to do next. So we're going to start working with real data here next. So Will's going to go through some examples here, and if you've been able to download this data, awesome. We're in the from the Google Drive. We're in the example data here. The data we're going to be working at is all structured in this tag data raw folder. It's an Antarctic deployment. This is how we structure our data. You can do it in a lot of different ways. But the main part is once you have your deployment folder here, and we'll talk about some of these ID information here later on. In your raw folder, which is all the data you download from your tag, you get all of these CSV files with the data, which we've been talking about so far. But now we're going to start talking about the video and the audio, and starting to get into the video and the audio part of the CATS tags. And so when these come out, the raw data here is just audio files if you have that capability in your tag. And the movie files have both video and audio. And you should be able to play those video and audio, and we'll give you a chance to do that later on, to play those. But one of the things we want to be able to do is the more we can kind of stabilize some of these things, one of the advantages of CATS tags is that they keep everything in a very raw format. So if you tried to put like a GoPro on a whale, which some of the early CATS tags did, you often can come back with a tag that like the GoPro just didn't work. Something got wrong in the video encoding process. And so the video comes back blank. You can see it, it's got 3 gigabytes and you're like pulling your hair out because there's tags there, there's data there, but you can't read it or process it. So the CATS tags come out very raw. And so these movie files can only be read in usually can only be read in a couple of different programs. One of them is MPCHC, which we have a link to on the workshop data files. And the other one is, and so we have in the code and tutorial materials, we have a lot of programs here. The VLC and MPCHC is the other one.
I don't know if we have MPCHC on there right now, just because I think it's a slightly depreciated. Like I think they stopped updating it in like 2017. But if you feel comfortable using that, we will put that on there. It's another video, basically another media player software like VLC.
Yeah, and we'll show you how here. It's actually one of the best ones because it can actually monitor your timestamps the best. But one of the things that we can do that Will's going to show you through next is this idea of how do you convert these movie files and actually strip the audio from them. So we're going to go into that and start actually dealing with audio data. This is where some of the processing of your computer is going to come into play. But we're going to start stripping audio. So we're going to spend the rest of the day kind of looking at how do we actually interpret some of these video data, and so that we can import them into our data stream and start syncing them with our data files. So I'll hand it over to Will with that information.
Cool. Okay. So I'm going to use just a few minutes here to sort of go through, like Dave's saying, a little bit of how you can use this program called FFmpeg to essentially strip your audio off of your video files and keep them as separate files. And so the reason you might want to do that is to check it to see if your audio is offset from your video at all. That's something that in some of the older versions we were finding some issues that the audio on a single video would be off by like 2 seconds or a second and a half or something by the end of that video. And so by sort of stripping the audio off and keeping it as a separate .wav file, you can actually sort of get around that. So I'm going to very quickly show that a little bit, and also use this as a moment to plug the GitHub wiki, which I'm not going to go through sort of the full flow right now. I just don't really have time, but all of the tutorial materials should be up there for anybody who would like them. So, all right, so very quickly, like I said, essential question here, why can't we use the audio taken directly from the video? Again, because there might be an offset in there that isn't really captured unless we have that .wav file separate. And then we do have some recommendations for the bit rate and the sample rate of the video and the audio. We recommend that you use a bit rate of 16 kilobytes or 16 kilobytes per second, and a sample rate of 48 kilohertz or less. Other settings will work. We just, we haven't had the chance to really test those extensively yet. And so this is what we tend to use, and works pretty well. So what I'm going to do here is just very quickly go through kind of like the intro steps on how to download this FFmpeg program. And then we're going to just check some WAV files really quickly to see sort of like how you could look for an offset and see if you are actually seeing one. So we're actually going to move over here now from GitHub, or from PowerPoint to GitHub. And so this is through the website, if you go to this code and tutorial materials and you go to the GitHub repository, you're going to find that right here. And so it's going to open this up, and this is again where all of the code is going to be stored. This is again sort of like a living document, but we want this to be a little more permanent even than you know the workshop. So if you go into here and then you go and you click on this wiki link, it'll take you over to sort of a full tutorial of what we plan to go through here, and sort of how to work through this process from beginning to end. And again, one more time, this is a living document. So if you guys go through here and you see that there's an error or something, or you see that there's something missing, please tell me. I want to fill this in and make it as useful as possible for everyone. So, you know, please let me know. So what we're going to do right here is if you go and you can see there's these pages on the side, and so they sort of correspond to different pieces of this process. So we're going to go to this raw video and audio processing right now, and we're going to see that there's sort of like this full tutorial on how to download FFmpeg and actually get it running on your computer, because FFmpeg runs through the command prompt or the command line of your computer. So it takes a few extra steps to sort of like set that up into your computer's path, so it kind of knows what to do. And so we're going to just be going through the first few steps here. So what we're going to do is we're going to follow this link. It's going to take us over to this FFmpeg download screen. We're going to click download here. And then for people with a Windows machine, we're going to kind of click through here and go to this gian.dev. And I think this might change every once in a while, but there's always sort of like these new builds coming up. And if you scroll down here, you'll get to this release window. And so you would click on one of these. I would tend to click on this .zip file. That just means you don't have to download some other program to deal with these .7z files. So you download this zip and you basically, you know, remove it from, you unzip it, put it in a place on your computer. And then what we're going to be doing here, we're going to just move down in this process really quickly. So then we're going to open up our system properties. So the way to do that is you open up your start menu. And this, I'm going a little bit quickly here, I know, but I just want to kind of get through the main steps of this process. So you're going to open up your system properties, as you can see here, and then you're going to click to open up the environmental variables. And what you're going to get is this screen here. You're going to go down below here to your path, and you're going to click to edit. And in here, you're going to see these are all the different variables, the path variables that are sort of like set into your computer. And so what we're going to do, and I already have it in here, but you're going to have this program files / mpeg / bin. And so that, you know, wherever you put your FFmpeg file folder on your computer, that's going to be the path that you want to basically like take that path and put it into here. And I'm working on, I think, Windows 10, so it might look a little bit different, and it's possible you might have to look up, you know, how to do this if it's significantly different. But this is the main gist of it. You want to go in here, add in this FFmpeg to your system path, and then you can sort of OK out of that, and then OK out of this, and then you should be good to go. So if I open up my command prompt, bring this over, so you can see I now have this wonderful black screen, which I am just, you know, figuring out how to work with, but I imagine some people have a little more experience with than I do. So you can see I have my system path here, and we do have some lines of code, sort of how to work with this and actually how to perform these FFmpeg steps. So, but if I just wanted to use FFmpeg, I could just type it in there. And there we see that since I set up my path correctly, the the executable files in the program are actually going to run. So all I need to do is set my path, and then if you use these lines of code and follow along these steps here, that should give you a sense for how to pull these .wav files off of the videos and actually create them separately. And I'm actually going to show you right here now. So I started off with these two videos, and I added in, or I used FFmpeg to strip these two audio files off. And so I'm just going to open up this audio file. And so we're using the program Audacity, which once again is in the is linked on the website. So we're going to import this here. And actually, while that's importing, I'm going to move back and I'm going to open up the video that corresponds to it. So this is the same video and the audio that was taken from that video. So I'm going to keep this here.
I'll just jump in to add on to Will's, like, so we're showing, I know we have a lot of acousticians in the audience, and so like you can obviously use whatever acoustic software you want. This is just one example of a way to check your WAV files. And so this is not something you even have to do every time. This is just a way to like say like, okay, we strip the audio, like, is it a good audio file? And so what if you just try to like do it with MATLAB or something, which is the way we used to do it, you end up with some offsets due to skipped frames, which we'll get into a little bit more tomorrow morning. But this is one way to like make sure you have maintain a video offset. So Will's checking those right now.
Yeah, so what I'm basically doing now is I've gone to the last surfacing, so when the whale surfaces in this deployment, and I've done that on the audio. And so I can see that there's like this really loud sound when the tag hits the water, right as it goes back in. And so now I'm going to look in the video, and using these timestamps at the bottom, I'm going to move along, and so I can see that this happens at 22 minutes, 14 seconds, and 409 milliseconds. So keep going forward. So we're going to start at about 14. So let's check and see. So right when the tag goes back in the water, we have that sound. So let's check it one more time. Right about there. So you see that we have 2214.550, 2214.409. I would say that's pretty close. You're not seeing, a second or two of offset, which is good. So, I would maybe check a few other videos, but if I'm satisfied that there's no offset, then I think we're good to go on this piece. Cool. So. Yeah, and we'll get into a little more tomorrow, I think. Some of the different ways that you can kind of check your data as you're going, and make sure that what you're seeing is accurate. And with that, I think I'm going to turn it back over to Dave for the movie time script before we have Ari come in.
Yeah. Thanks, Will. I will just kind of emphasize. So basically what you're trying to do there, from what Will said, is create a bunch of WAV files, essentially, right? And so those are the audio files that we're going to start reading into our data coming up here soon. The other piece that we need to do with our videos is looking at the movies a little bit, starting to look at how the movies work. So I am every time. So one of the big things we're trying to figure out, right, the whole purpose of a lot of this workshop that's different than just typical tag data is how do we efficiently align video and data? So one way is using external programs like Will just said to like strip off the audio to actually get a good audio read. And then the next thing we have is the first step of the CATS PRH process, which we'll show you. Your homework tonight essentially is going to be to try to run this because it's the kind of thing that runs overnight. So your first step, your homework tonight is going to be to try to get this file that creates this movie time script. And what this movie time script does, and just to read some of these where you can understand what's happening here in this CATS tag, the download ID is when you download a tag, it has this code on there. And the code is just the download time. It doesn't have anything to do with the deployment necessarily. It's just going to, so just so you get used to seeing these things. So this just means that the tag was downloaded. We recovered the tag. It was downloaded in 2020 on March 13th at this time. And then all of the data has the same timestamp on that tag. And then, so when we use the tag ID, that's something you set in the UI to help keep track of your tag ID. You can set that to be whatever you want. We usually have a number. We just say cats and then the number every time, but you can set that however is useful for you. Contrast that with the deployment ID that we use. And again, you can use whatever format you want, but this is the way that we do it, where you have a species ID at the front. MN stands for Megapteron evangeli. So it's a humpback whale deployed on this date, 2020, March 12th. And then the tag ID is that tag number 58 to help keep track of if we have multiple deployments on different days or whatever with different tag numbers. So that's how we keep track of our different tags and different days. So when you see those numbers thrown around, that's what's going on here. What we're trying to create from this movie times, what you're going to try to do as your homework tonight is run this movie times file to get these different pieces here. This is essentially stripping off of the videos. What is the timestamp of every video? That's what this key is, this frame times script right here, the frame times variable. The VidDN is the start time of the video. The frame times is like the actual timestamp of every frame of the video. And the reason we have to do this, I have an exercise to help show you guys why we have to do this. But the reason is that because it's not always obvious that, because not every, like I said, these tags have raw or encapsulating raw data, meaning that they maintain the data, even if there's an error in there. And so that means sometimes there's a skipped frame, like, oh, okay, which video processing does all the time because there's like there's a bright light or a bright flash or something like overwhelms the processor in the tags. And so to kind of compensate for that overwhelming of the processor, we've written these scripts to kind of read the frame times off of each tag. So the way we're going to do that is we're going to open up a MATLAB with this main cats PRH tool. And it has a couple of settings in here that you can set to help you read your information, read your timestamps off of here. So this script does two things. So this is kind of our main PRH tool. I'm going to actually open up a MATLAB here so you can just kind of see it in the actual environment. Because what we'll have you do is actually run this tonight. This is the main thing we're going to be using for the rest of the workshop, essentially. And this is what kind of starts to create your video files. Just as a versioning thing, when you open this up, one of the things I put up here is in different versions of MATLAB, it can handle errors in different ways. Hopefully you never have to use this. Hopefully you don't do a lot of error checking, but just if you're not used to using it, old versions of MATLAB used to have this breakpoints up here where you can like set it to stop on errors. And so it'll stop within your code. And then you can kind of error check here. If you start doing error checking in newer versions of MATLAB, you have to run this code every time. So that's just up there at the front, what that is. Then basically this is set up in cells like that example earlier, where you have these different functions, and this is those step 1, step 2, etc. And we have different descriptions of all of these different steps on the GitHub, but they're set up to run one at a time. So your homework tonight is to run this first cell, and there's some information here about like what the outputs are and what the expected outputs are and how long. This is a cell that takes a long time. So it's going to create this movie times file. And the other thing it's going to create is an audio data folder with the WAV files and audio information for each file. So you have to run the step that Will said first in order to get WAV files. If you were not able to, for some reason you can't get the FFmpeg to work, or that's giving you problems right now to strip the WAV files, we recommend, I provided the WAV files for you in the workshop day 1 materials here off the Google Drive. And so you could copy those into your example data folder. Into your tag data raw, into your example data folder here, and just put it into this raw folder, put that WAV files into here if you were not able to download the data. But the idea is to put in the data files into here, and then you run the script, and what it's going to create is a folder that looks like this, just so you can kind of see the output. This is all of our data files here. Let that fire up. It's going to create an audio data folder with WAV files and audio for all your things, as well as that movie times folder, movie times file, which has the frame times in there. I'm kind of stalling because we're in this intermediate time period where we don't have time to do the full activity I was going to plan. So tomorrow, what we're going to start with is this this worksheet essentially that helps you understand what these frame times are. So we'll go through this tomorrow that kind of looks at the actual how you read these timestamps. What does that frame times variable actually do? How can you read that from a variable? So what I'd say is your homework for tonight is A, if you can, try to run this first script using the setup, using the GitHub setup here. So from your GitHub file, try to download all the data here. Then in the wiki here, there's information on importing raw video and audio processing that Will kind of went through today. So you can look at that file to kind of get your start on that section. I know we're skipping around, but that's because we're kind of thinking about how do you process the data and why. So we're starting with this raw video and audio processing. And the main goal is to try to run this script. And the way to do that, if you've never used MATLAB before, just as a quick introduction, if you've downloaded all your data into a GitHub folder here, you need to add this to the path. So you have GitHub, and then you have your CATS MATLAB tools here. And you need to right click on that and add that to the path, all of your selected folders and subfolders. And then that'll recognize all of the scripts that you need in here. So once you have that added into your path, you should just be able to run this section here. And what it's going to do is going to direct you to select your movie times files from the deployment. So you can navigate to your movie times files. I have this tester file set up in here, and it's going to navigate to that first video file or audio file of the deployment. So I'm just going to select the first audio file of that deployment. And then it's going to ask you to select the other files, and it's going to run. If you have all your WAV files set up in your WAV file bin here, it's going to create WAV files as well for these audio files from the raw data using the information about the sample rate and stuff that was in your WAV files that you stripped from the videos. So it's going to create those audio files, and then it's going to make that movie times file, which has the frame timestamp of everyone. So that's the goal, is to set that up tonight. We'll see if you guys have success with it or what errors you have. I'm curious to see if you can run that on your own with these steps. But that's the goal of what you're going to try to create tonight, is run this first step of this main CATS PRH tool. Just to say one more thing about that is that you have these settings here that you can do to help you. All of these cells are set up with various things to set up at the beginning of the script. So some of them you can usually often just run the whole thing, but sometimes you want to change something. Like if you're having processing problems where like your computer isn't really up to snuff to handle this, you can shorten the duration that it reads of every video. Or if you have this like a supercomputer, you could read a minute at a time. So this is just the duration of time it reads in increments of timestamps every time. And it takes a lot of memory from your computer to run that. This is the folder where you start looking for paths. So that's just an option to help you set up, to help you find the data that you're looking for. And then there's this idea of reading audio files. So if you've already read the audio files once and created all these WAV files, then you don't have to do it again if you had an error or something, or you're trying to rewrite just a small part of it. The rest of these you probably won't ever have to set up, but there are options there for kind of advanced users. But that's the main thing. See if you can run this file. The way these are all set up is that you have this one workhorse script, I call it, that is basically the script that it's trying to run, which is this make movie time script. And they're all located within the this kind of the structure here. Is that within your, you have your main scripts here, your main CATS PRH tools, and then you have your workhorse functions, which are all the functions that it's calling, just so you can kind of see those functions and work with those when you're doing these scripts. But that's the main thing that it's trying to do there. Okay, that's all I really wanted to say about that. Do we need so question in the chat, do we need all the toolboxes installed before we run the script? Yes, you want to have the toolboxes installed. There are some sub-functions that run, including this make movie times, and it has sub-functions in it that it will run. And so the idea of having the whole GitHub installed is that then you shouldn't have errors with finding sub-functions that aren't on your path. We should have provided all of the tools that you need in order to run this script. The other question was, do the WAV files have to be in the same folder as the movie files? Yes, I just put them in a WAV files format in there. Cool. If there's no other questions on what to do tonight, to try to run this script overnight, I'm going to turn it over to Ari here for kind of a final wrap up on some biologging ideas. And then we'll end with a quick poll at the end again. So stick around, but we'll turn it over to Ari here for kind of a wrap up on biologging. But we'll give it a second too if there's any other questions from anyone? You guys have been awesome. It's really good. Thanks for being here and patience as we navigate day one here. Okay, well then it's my pleasure to introduce Ari, who will just talk a little bit about some of the things you can do with biologging tags and some of the ways to get us excited about, kind of wrap up again with this break from coding to think about like, well, why are we doing this? What's the purpose of why we're getting out here and doing this cool science? So we'll turn it over to Ari, and then we'll do a quick closing thing when Ari's done, and then we'll be done for the day. So good job, guys.
Great, thanks, Dave, and thanks to you and Will and everybody else who's helped to put this project and this course together.
I want to interrupt you, Ari, just because I should have done a better job introducing Ari. Sometimes I assume that, Ari Freelander, everyone knows Ari Freelander in the marine mammal community, associate professor at UC University of California, Santa Cruz, and has been doing this biologging stuff for a long time, putting tags on a lot of ways. As Will said earlier, one of the persons probably placed more tags on animals than anyone else around. And so really an expert in the field and my current PhD and my current postdoc advisor. So take it away, Ari.
Cool. This is an awesome class. I really wish that these kinds of things were available back when I was at the age where I could actually learn this kind of stuff. It's amazing how quickly this stuff has passed me by, sort of in the analytical realm. But I'm excited to be here. I'm super excited about these tags and what they've been able to do and what I think folks can do with them moving forward. And like Dave said, what I wanted to do is just kind of talk for 15 minutes or so and sort of share some of my thoughts and ideas on the tools that we have and how they've evolved and how I think we can begin to ask and answer questions using these kinds of tools, and the things that myself and my colleagues have done that I think have been kind of interesting towards learning a little bit more about these animals and the context around how they operate in marine ecosystems. So let me just share my screen and I'll fire up a little presentation. All right, excellent. I was also excited. I looking through the folks who are online, and I see some old friends and colleagues and some students that I've worked with in the past. I'm really excited to see them, and I'll try and shout out folks as much as I can who are working on some of the projects that I'll talk about. To me, the real message here is that these biologging tools allow us to explore the ocean and the animals in them in ways that we probably don't even know that we can study them in. I certainly was quite naive when I started doing this kind of stuff about what the what the possibilities were, and it's been over a long time that we've learned how we can use these tags the most effectively. The thing that I'm sure Dave and Will have mentioned is that these kinds of things take an enormous amount of energy and resources and commitment by people, and I'm really proud of the fact that all the work I'm going to talk about today has been done by colleagues in I don't know, 15 or 20 different countries, 20 or 30 different organizations and institutes that have helped to either support different projects or the development of the tools that we use. And you guys are going to hear from a lot of people from a lot of these places today. So just want to sort of reiterate how important it is to have a good colleague network and to work on teams where everybody has different strengths that they can bring to the table. One of the things to me that's really great about marine mammals is that there are a myriad number of ways that we can study them. And depending on the questions that you're asking, you need the right tool for them. And this is a page out of a report that we did with WWF a few years ago that just sort of lists out some of the main ways that researchers study animals in the field. And obviously, it's clear to you guys, but it's worth kind of thinking back on this, that you need the right tool for the job. If you want to measure the length of an animal, a tag isn't the best thing. If you want to look at the sounds that an animal makes, a tag might be the right thing, and maybe passive acoustics are another good thing. But it really depends on the question that you have. And tags provide a nice rabbit hole to go down to study the underwater behavior of a lot of these different animals. You guys probably heard a little bit about the evolution of tags, and Jeremy will probably talk a little bit more about this. But in a very sort of short window, this all started, biologging started with Jerry Koyman in 1963, 1964, when he sort of modified a kitchen timer and put it on a Weddell seal in the Antarctic and measured the time that an animal dove and the depth that animal went to. And I was very fortunate to come around, not in the 1960s, but right around 2000, I started doing work on tags with this guy up here, Mark Johnson, as well as with Susan Parks, Doug Novacek, Peter Tyak. The folks who were at Woods Hole and MIT at that time, where the first of these motion sensing and audio recording tags were developed. And on the bottom, you sort of see the three generations, the 3-cup version 1 D-tag, the version 2 D-tag, and then the version 3, which is a bit smaller. And these were really the first instruments that allowed us to measure multiple things about the animal and its environment and some of the context around what the animals were doing. And the first project I was involved in was a behavioral response type of study to understand how right whales either made sounds or responded to sounds of incoming ships. And in order to do that, you needed a tool that could measure what the animal was doing, as well as the environment that the animal was perceiving. And in this case, it was through audio channels. And so those acoustics were a huge component of those first tags. One thing, though, that left me a little lacking as a very visual person and not an acoustician was some other sense of ways to visualize these animals, the data, as well as the environment around these animals. And not long after this, we started partnering with Greg Marshall and folks at the National Geographic Society. And in the upper part of this slide, you see an emperor penguin carrying what's called a critter cam. And this was one of the first video recording tags that Greg Marshall developed, tested it out on himself and his kids in a swimming pool in the 80s, and eventually started putting it on other animals. And this was a great tag because it gave us that first glimpse from the animal's perspective of what it looked like to be there. And I think that was a very intuitive thing that was able to bring a lot of people into the field and generate these kind of emotional responses and actually stimulate ways to think about what that could be used for. Unfortunately, these critter cams didn't have sensors in them like the D-tag did, or even a pressure sensor. And so it wasn't until we were able to work with the folks at CATS to develop a robust tag that included all of these components that we sort of were able to expand the horizons of what we do. And it was because of Peter and Nico, Jeremy and Dave. Adrian Glees was the first person who introduced us to CATS tags, and they put those on sharks. That really opened up a world for us that I'm excited about and hopefully can share a little bit of insights into. Tagging has evolved over time. The picture on the left here, this is Tom Hurst, one of the original engineers with the D-tag, and that is a 42-foot cantilevered carbon fiber pole that is mounted on the front of an inflatable boat. This was the original way that we put D-tags on whales, was using this massive, very cumbersome device, but it was great because you didn't have to be very close to the whales. On the bottom is sort of when I got into things, what I started to do, and this is about a 12-foot little inflatable boat with myself and Dave Wiley. I think Mason Wanrich took this picture. We were pretty dumb. We tried to get up close to these whales in a teeny tiny boat with a really little pole, and it worked for a few species that are easy to get to, like humpback whales. But in the upper part of this sequence, you see what it's like to try and tag a rhesus dolphin. You can't get close to some of these animals, and you end up having to do some kind of gymnastics to get near them. So we've learned over time that there's not sort of one way to skin this. What works for one species may not work for others. And getting out there and using these tools in the field is really the only way to what works best in your situation. So if you're seeing things from one species here, don't think that it either applies to your species or can't be done with your species. Up until 2014, we had never tagged a minke whale. And thanks to Jake Levinson, who I saw on here, he gave us one of his AccuSounds to bring in the field. We put that on a minke whale, and then we crapped our pants when it went under the sea ice, and we thought we were going to lose Jake's tag and owe him a lot of money. And luckily it stayed on that animal, and we got the tag back and started a whole new avenue of research. But there's been so many kind of firsts along the way of putting tags on animals and understanding what you can learn about them, that's really what gets me excited. I feel like tagging has sort of evolved under these sort of three sort of statements. And I'm going to sort of walk through how I think we've gotten there. The first thing is to just certainly understand what are marine mammals doing underwater. You put a tag on an animal, it'll tell you the depth, it'll tell you the time, it'll tell you all of these things about what the whale is doing underwater. But then there's also this complexity of how these animals are doing it. And the work that Sherelle talked about probably, that Will is doing, that Dave has done, to try and understand the kinematics, how the animals are doing it and how the adaptations that the animals have allows them to do these kinds of things. But then to me, the ultimate question is, why are they doing these things? And this is really where I think the CATS tags have opened up an avenue for us by seeing from the animal's perspective and being able to see some of the environment around the animals, as well as sampling oceanographically or concurrently with other sensors. We get that context for why animals are doing certain things. And I know Dave mentioned that at the beginning, that this contextualizing the animals and why they do things is really, to me, the most most important thing that we need to understand about how these animals do things. And so these are the tools that we use to do that. I feel like in order to understand what the animals are doing, we need sensors to measure animal movement, and we need the analytical tools to help organize the data. It also helps to have a knowledge of the animal so that you understand what it is that these animals are doing. How? That question to me requires tools to be able to visualize the data. And Jen's going to talk about track plot later in the week. I'll mention that very quickly. But this also requires sort of a different level of knowledge of the animals, like their physiology and their anatomy, and why a baleen whale is able to lunge feed and how it's able to lunge feed requires knowledge about the size of its mouth and the musculature and the control surfaces. And then that why question to me requires these contextual variables from the environment. These can be biotic or abiotic, it can be prey mapping, it can be sea ice, they can be intrinsic or extrinsic. And we need to generate these from in situ measurements that can either be done on the tags or from the video cameras that are now on the tags, or from independent measurements using things like echo sounders or oceanographic ships. And depending on the question that you're asking, you just want to make sure that you have the right tool to be able to address that. So obviously, you guys are here for these CAT tags, and I really can't stress enough how important that inclusion of a video camera with these motion sensing tags, as well as georeferencing, has made things. You can see what an animal does underwater, but unless you can place it in space very accurately, the measurements that you get about the environment and linking those to where that animal is may be spurious or may tell you things that are sort of non-informative. But to me, that video camera and being able to see from that animal's perspective, how many other conspecifics are around? Are there other things in the environment that are in front of that animal that may help to justify or represent why that animal is doing something? I think is a really important thing. And so you guys are going to learn about the tools to put all those pieces together, and then hopefully you can use those to create your own experiments or go out and do your own science in the fields and species that you work with. One of the reasons that context I think is really important is when you're studying animals in sea ice, for example. And so this is us putting a tag on a minke whale. Jeremy Goldbogen took this great video with his iPhone. But if you didn't have a video camera on the tag that you put on this animal, you wouldn't be able to see that surface of the ocean. You wouldn't be able to see that an animal didn't go to certain places because there was sea ice. And you wouldn't be able to tell whether or not the environment that that animal was in impacted whether or not they were feeding or traveling, or how much of each of those they were doing at a time. So being able to integrate that, I think, is really important. The other thing, and I know you guys have seen this, is confirmation of certain behaviors, and just being able to use the sensors to corroborate what we see on the tags is really important. Blue whales are sort of at one end of the spectrum here, because that kinematic signature, the animals are moving so quickly and they're so big, and the signatures express so big, it's really difficult not to be accurate in there. But then you might work with something maybe like an Odonocete that doesn't have such a kinematic signature when it feeds, or a humpback whale that's feeding on the bottom that may not do the same kind of acceleration. So having a video alongside with the tag sensor data to corroborate the things that you're seeing not only is intuitive, but I think it's important for validating what we find in the tag sensors. Track plot is something that I know Jen is going to talk about a little later, and this was a program that was developed by Colin Ware at the University of New Hampshire, and he built it after sort of, here's Buckwheat, my dog, if you want to say hi. Colin built this program as a way for us to visualize the three-dimensional motion that we were getting from these tags, because we were studying bubble net feeding behavior in Cape Cod, and we wanted to see, did all animals make bubble nets in the same way, and how did they use space differently? And this was sort of one of the first tools that we used to visualize the track of the animal, see how much motion they're using, and see what kind of space they're using. And this was really great for that sort of exploratory thing about how animals do certain things. But then providing that context to why they did them, to me, was sort of the next leap that we were able to make. This is a video, I'm sure Jen will show you something similar to this, and so I don't want to kind of steal her thunder. Okay, so a couple of the other contextual variables that I think are important are things like physiology, and Jeremy will probably talk a little bit about this, but we've started to integrate things like heart rate into these tags. And so if you can understand that an animal like a blue whale feeds 5 or 6 times on a given dive, comes to the surface, exchanges oxygen, goes back down and does that again. If you're interested in the energetics of that animal, the metabolism of that animal, understanding the heart rate that is sort of goes in concert with the different activities, tells you a lot about that animal, what it's capable of doing and what its limitations are. And so adding in these physiological sensors to link to the behavior of the animal can be very powerful. I know there's been some recent work with harbor porpoises using D-tags and heart rate measurements that are going to make a really cool foil where you have the smallest and the largest marine mammals out there. And we're now able to put context to the energetics of what those animals are doing. To me, the biggest thing that I've been interested in is understanding sort of how prey in the context of the environment around an animal impacts what it's doing. I know there's several students on here. I saw Ellen Chenoweth, I saw Teresa Kirchner, are students that use similar kinds of data and tags to look at why animals did certain things and why they fed in certain ways, vertically in the water column at different times of day, even the different motions that the animals do. And in order to understand why they do that, we really need to be able to map things like the prey using echo sounders. With blue whales, for example, we've been able to show that when blue whales find large and dense patches, they can lunge in a very straight, kind of straightforward manner. But when they're targeting smaller patches that are less dense, they do a lot more kinematic motion, like 360-degree rolls and very acrobatic maneuvers. And without that context of the prey patch around it, we wouldn't have an understanding of why animals were doing something different on different kinds of dives, but also we wouldn't know about the consequences of those. The consequences of those are that animals can be more efficient depending on the density of prey that they find. We've done some work with fin whales, and the example here on the right shows that when fin whales target different densities of prey, they're able to consume 4 times more prey when they feed on deep patches that are dense versus shallow patches that are less dense. And that lets us think about things like optimal foraging theory and where the animals are getting most of their energy. It can also help us think about disturbance, and when animals are disturbed in their environment, what things may be more important to them or have greater consequences. Some work we did with Elliot Hazen, and I just want to sort of end on this figure here, was really interesting. And what we did here was to look at how animals conserved oxygen or used oxygen relative to the density of prey that they were feeding on. So we were able to measure different prey densities around where animals were feeding. And what we were able to show is that based on the metabolic rates of these animals and understanding their physiology, when they were feeding on less dense prey patches, they were conserving oxygen and they were basically just scraping by. But when they found high density prey patches, the animals increased their energy of oxygen at a cost because the food was so enriching for them. So the animal's making a trade-off to feed on very high density prey, but limit itself in terms of its oxygen stores. And we found that blue whales didn't find these prey patches that were super dense all the time. So when they did find them, they had to maximize their energetic gains. Additionally, on top of that, and you're going to hear from Stacy DeRuyter, I think later in this week, Stacy was one of the people that worked on understanding the consequences of behavioral responses in blue whales. And what we were able to find when we played sonar to these animals was that blue whales actually were disproportionately likely to respond to sonar when they were feeding on deep patches. So a tag that had acoustics on it, where we could measure the sound that an animal was actually receiving, and all the kinematic sensors as well as measuring the prey in the environment, allowed us to say to the Navy and to these other places that use sonars, blue whales respond to sonar, and they do so during a period of time that's energetically critical to them, and they don't respond in periods of time where they're not gaining energy. So by understanding the context of the environment around the animal, the behavior of the animal, and then measuring a disturbance that was impacting them, we gained a huge amount of insight into not only how the animals operate, but why they do certain things and what the consequences of those can be. I mentioned blue whales sort of moving around in space. And we had a kind of a couple of papers that demonstrate really, again, the sort of value and utility of measuring prey. So on the left here, you have these still frame images from a critter cam that was put on a blue whale. And what Jeremy Goldbogen showed was that this blue whale, as it approached this very small prey patch from below, did so and did these 360-degree rolls. But without a kinematic sensor inside the critter cam, you couldn't necessarily say that it did a 360-degree roll, or at what depth this animal was doing it at, or what the pitch angle was. And then when we integrated CATS tags into this, we were able to reproduce the image that you see on the right. And what we were able to show was that, in fact, blue whales not only did 360-degree rolls when they're targeting shallow and less dense prey patches, but they do so in a way that is antithetical to how you would expect the animals to move. All animals in nature that have been measured that show a bias or lateralization for behaviors tend to do it to the right side. And blue whales, we found, actually rolled to the left side when they were doing these 360-degree maneuvers. We were able to show and demonstrate the functional reason why they did that, because we had inertial sensors on the tag and because we were measuring prey at the same time. So where Jeremy was able, and we were able to describe in very general terms what the animals were doing with a critter cam, it wasn't until we had prey data and we had a tag that measured the animal's movements that we were able to put that whole story together. So in a very rapid assessment, and hopefully this is sort of things that you can bring with you guys through this week and then onto your own studies, biologging tools first and foremost allow us to explore nature and explore these animals and explore the oceans that these animals are in. And I think that's absolutely the most important and fundamental thing that we can do. They help us to tell stories about the lives of these animals, the environments that they live in, to gain insights as to how they do different things and how they make a living and how different environments and different species do things differently. But it also helps us mitigate and minimize the negative impacts of human behavior. Now, those D tags in 2000, when I first started working, I mentioned those tags were developed to try and better understand the impact of sound on right whales. And that hasn't changed. We're continually doing more and more of those kinds of studies to understand how humans impact animals. And by having sensors that allow us to measure human activity in the ocean, either via sound or via remote sensing, we can get a much better understanding of animals, why they do things, and how we can to them. So hopefully these are different strategies that you'll take in the different courses of research that you have. And Dave and Will are going to give you guys the tools to be able to do that in a much more straightforward way than we've ever had up to date. I worked with DTAGs for, I think, 8 or 9 years before we had a workshop where we're able to talk through the data processing and structuring like you guys are getting today. So I hope you guys take advantage of this week. I hope you take advantage of everybody who's instructing in all of their expertise. And I hope that I can be a resource for folks too, if they've got questions about putting together projects or how to do things or how to sort of the logistics around this. But the quantitative tools that Dave and Will are going to talk to you guys about are far beyond me, and certainly something that these guys are the experts in. So I'll leave you with this kind of fun video from Monterey Bay, which again, to me, really expresses what the value is of having this context of a video. You see the environment in Monterey Bay with all these sea nettles and humpback whales swimming through them. And then you start to see other animals like these California sea lions that are feeding in the same time in the same place as these whales. And so we can get a much better understanding of the ecological interactions between these species and what happens in the ocean outside of just the animals that we tag, but the environments that they kind of maneuver through. So happy to answer any questions. My contact details will hopefully be available if you guys have questions outside of this. And I will pass it back over to Dave.
Thanks, Ari. Oh, I should keep that video going. Thanks to everyone for being here. That was, I know it's a lot, but the idea is to get everyone from the raw data to all that stuff that Ari just showed and all those the cool end results there where we're doing good science with it. So we'll keep working through it tomorrow, and Wednesday we're going to really hit to some of the code pretty hard. So hopefully you're able to run that script tonight. I did have an exit poll I put into the chat. So please, if you get a chance to fill that out, great. And we'll see some of you guys at 2 o'clock for the MATLAB intro workshop. Everyone else will see tomorrow morning, or morning my time. Thanks, guys. It was awesome.
Will the MATLAB workshop be recorded?
For anyone who, I just saw a couple of questions just come in at the end. For anyone who's still here, we are recording these MATLAB, all these things. Oh, the MATLAB workshop itself. It is, it will also be available. There's a bunch of tutorial materials online that we can send you to the link again for the MATLAB workshop. So we'll make that whole workshop available if you want to try to work through that on your own time. Someone else, go ahead, Will.
No, I was just, yes, and it'll be the same Zoom link for the rest of the week.
Yep. Same Zoom link, same bat time, same bat place. And I had another question about Max for anyone who's using Max. Max should work for all this stuff, but I have not tested it on any of it. So if you have Max specific problems, I'm not sure that I can help you very much this week, unfortunately. Cool. Good to see everyone. I'm going to exit out of this room for now, but it should actually stay open.